I think next one will be held in Bangalore next year. So we do it odd and even years. We do have, as someone has mentioned, student mechanism design contest. So it started 2009 at NIT Durgapur with savings. We had it in 2003 at IIT Delhi, but now I think the organizer take care of it. That money got exhausted. So I encourage all participants to become, AMM member. Professor Saban is the treasurer of AMM also, sitting here, who is the organizer, and take active roles. In fact, for the last couple of years, we are also trying to have similar bodies to work together. Professor Murthy was asking how big is this community. I said not so big, though, maybe in hundreds. So the similar bodies should come together, as all of us know that collaboration is the day. And I'm sure two of the bodies which we am targeting, the ISM Indian Social Mechanical Engineers and then the Robotics Society, I requested them to come tomorrow during our GBM. Now, I'd like to mention a new initiative of AMM, which has decided earlier, I think possibly last NACOM, to introduce a Lifetime Achievement Award. So for that, we created a committee consisting of me, and then Professor Ghoshal, who is sitting here, Professor Kurian, the IAST, ex-IAST, and Professor PM Pathak for IIT Roorkee. So we had several nominations, and based on that, I am glad to announce, Professor C. Amarnath, we are honoring this year. So a big hand for them. So I request, maybe someone can accompany. Um, Professor Amarnath to be escorted. Maybe someone can escort him. Rajiv. And I would request Professor Murthy to felicitate with a Katsal. After this, citation is separately. This is extra copy. So let me read out the citation for him. Association for Machines and Mechanism Lifetime Achievement Award on the 8th day of December 2025. The citation is awarded to Professor C. Amarnath for his contributions towards inception, nurture, and growth of AMM. He had an active he had an active role in building the AMM governing bodies over the years by leading from the front and for all selfless efforts in making AMM an internationally recognized body. He has also motivated engineering students to innovate. We, the president and the members of AMM, feel proud to honor such a doyen in the field of mechanism. No, President. Thank you. Big hand for him. And I would request now, uh, Director and so with this, I formally request Professor C. Abunnath to share a few of his experiences in front of us. Sir.
Thank you. Welcome to this conference to all of you who have gathered here. This conference began in 81, and once the conference began, I was wondering what are we doing? Because there was nothing, no manufacturing, nothing, very sparse among the student community. So I said, let me start one thing. There are two reasons why AMM was set up. One was in 83, International Federation of Theory of Machines was coming to New Delhi. IIT Delhi, and nobody knew what is this area of machines. Okay, so I said let's conduct a local conference in the country, and that's how AMM came into existence. We conducted, and ever since then, the conference has been conducted every alternate year. It became a big success. And the second problem which I faced was none of the students had any clue of what a machine is. They'll give you all sorts of stories of what a machine is. I said, we have to do something about that. So I called them and said, you will be surprised if I tell you the stories of what happened when I called them together and said, build something. Just gave them a clue as to what they should build, and that's it. They have to do it. Nothing was, no guidance was given, nothing was given. Believe me, yet despite all that, they did what I thought must be done. That's it. So that gave me the confidence that we can push this along through holding these conferences. One conference in INACOM, looking at the theory of machinery building, and the other conference is IPROM, Industrial Problems in Machinery and Mechanisms. Two conferences, one based on theory, another based on practice. So you are now attending the one based on theory. Next year, the one based on conference will be held at uh, where is it? Bangalore. No, I am looking for. Yeah, he has gone somewhere. Yeah, he is here. He is the one for the organizer for the IPROM next year. So my request is please attend. We need desperately people who can push this area forward. We're just having, I mean, we're not trying our best to push the area forward. That's what I can say. So I request you all to join hands and help us push this area forward. So thank you very much for having come here, for having listened to me, and I hope you will be able to. I can tell you many more stories of how the baby was born and how the baby grew and how the baby is still remaining a baby. Okay, so please do come to our conferences and encourage us. Thank you very much.
Thank you, Professor Saha. Thank you, Professor Amarnath. Let me also place on record our sincere thanks to our sponsors as we come close of the session. ANRF and DRDO and our industry partners, Recordine, Meganet, Ready Sim and Dice for their generous support. Without them, this conference would not have been possible. And to all our presenting authors, thank you for choosing INACOM 2025 to share your work. There is no conference without you. To all our participants from both near and far, we are grateful that you chose to spend these 3 days with us. We know that travel and scheduling was not easy, particularly this week. We hope that beyond the technical sessions, you will have time to experience our campus, interact informally with colleagues, and enjoy social events which we have planned. Once again, welcome to IIT Hyderabad, welcome to Telangana, welcome to India, and welcome to INACOM 2025. I wish you all a very productive, enjoyable, and memorable conference. With this, we formally close the inaugural session. I request the dignitaries to kindly take the seats in the audience. Thank you. The next session is the Professor Belgaonkar Memorial Lecture, which would be in this room, Audi 1, at 10 a.m. Thank you.
There are some refreshments like those who wants to take tea and coffee. There's right outside. You can go and take.
Huh? But you want to focus? We'll do it right after. We should.
very good morning to everyone here and those watching us live. It is my pleasure to introduce the speaker of this year's Professor Bilgaonkar Memorial Lecture. Please join me in welcoming Dr. Prasanna Gandhi. Dr. Gandhi is a professor of mechanical engineering at IIT Bombay. He is also the professor in charge of IITB Monash Research Academy and of Suman Mashruwala Advanced Microengineering Laboratory at IIT Bombay. He received his master's from IITB in 1996 and PhD from Rice University in 2001, both in mechanical engineering. He started his independent career at IIT Bombay in 2001. The current focus of Dr. Gandhi's research is on the dynamics and control of ultra flexible mechanisms, robotics, polymer and ceramic 3D microprinting, control of fluid instabilities for spontaneous multi scale manufacturing, leading to applications in microprinting, microfluidics, medical robotics, products, and devices. Some of the technologies developed in his lab in the past are transferred and licensed to ISRO, a few private companies, and a startup, FlexMotion Technologies, he co founded recently. Among other honors, he is a recipient of Robert Lowry Patton Award at Rice University, Boys Cast Fellowship of Government of India, Professor J.R. Isaac Fellowship, Best Faculty Award, FIE Foundation Award at IMTEX, P.K. Patwardhan Technology Development Award, SERB Technology Translation Award, Dr. Abdul Kalam Technology Innovation National Fellowship, and the Chandrayaan 3 honor. Towards social commitment, he is a certified teacher of stress relieving, art of living techniques since 2010, making a positive difference to the lives of students, householders, and professionals alike. Professor, the stage is yours.
uh, Distinguished guests, researchers, and students. It's my profound honor to be delivering this Professor B.M. Belgaonkar Memorial Lecture today at 22nd NACOM conference and 7th NACOM. Okay. So, as you might be aware, uh, Professor Belgaonkar was one of the founding members of IFTOM. When he stood in 1969 among 13 other members uh, for founding this organization, he was not only representing India, but he had a vision. Is the vision to kind of cooperate, work together with international researchers to advance mechanism science for industry and for society. At his time, probably mechanisms would mean like rigid joints, rigid links, and their motions relative to each other. Uh, Now, today, I'm going to talk about something that he might have that time may have been surprised to think about, or at the same time have been delighted also to see mechanisms without joints. Okay, so that is what we are going to talk about. We are going to discuss in this talk today about compliant mechanisms. Okay, and this is one of his. There is small delay in the. Yeah, it's one of the pictures, rare pictures of him at the second World Congress on Theory of Machines and Mechanisms in 1969, the same year this IFTOM was founded. is one of the founding fathers of this society. Okay, so I'm going to talk about these compliant mechanisms today with this short outline. So why we worry about compliant mechanisms? Okay, some of you, like in this conference, there are actually some sessions that are happening on compliant mechanisms. So some of you may be already aware about the importance of them, and we'll focus on many different applications that particularly have been developed for industry and lab kind of a scale purposes here in our lab. And then we kind of get into a little bit more on the mathematical details of some application that we have developed. And I hope to kind of leave you with a sense that, okay, oh look, this high deformation compliant mechanisms is going to be, like, very interesting for many different applications to come, and these fundamentals that we are talking about today could be, like, founding stones for future developments in the area. um, so as you know, these compliant mechanisms work with the bending of the linkages, or bending of, like, small deformations of or small or large deformations of compliant elements or flexible elements in the system. And they may be joints, they may be, like, complete link flexible. There are many different kind of, like, varieties of them. A lot of researchers have actually, and there are some people sitting in this audience here who have already, like, looked at this topology optimization based ways of development of very innovative kind of compliant mechanisms. And some of them pictures that you can see here, um, they 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 are also, like, there in the day-to-day activities. Okay, you can see them in the staplers. Some of the staplers will now come in the based on compliant mechanisms, umbrellas, and, like, many different kind of devices that you can relate to in the day-to-day life to these compliant kind of a mechanisms. And it's kind of very vast field now, like, that as we talk about. Okay, and so far, like, the industrial use of these mechanisms have been there, but, like, not so wide, I would say. So we'll look at some of these ways of, like, these mechanisms, not like, very complex mechanisms, but simple mechanisms, but, like, how do you kind of, like, generate their potential for, like, or advance their potential for the industrial applications. As you all know, the advantages that these mechanisms bring into table are high resolution, superior repeatability. When you give the same force, like, same displacement would happen, no friction, no backlash, no wear and tear that will be there in these systems. Because of that, there will be no lubrication that is required. So from the industry perspective, like, they'll run for, like, edges together without any maintenance. So there is, like, highly attractive proposition for industry, that you don't have, like, maintenance costs, or, like, they'll run for long duration. I mean, some of the mechanisms in our lab are now running for about, like, 15-20 years without any kind of requirement of any intervention. uh, so then also, because of low inertia, they'll have a higher speeds and low power requirement. All these are, like, very highly attractive advantages from next generation in robotics and automated kind of automation systems. However, they come at a cost. What is the cost? The challenges there are, like, these complex analysis and dynamics of these systems. Okay, and then also there is manufacturing difficulties that are there in these mechanisms, especially at the larger scale. Now we have a 3D printers that are available for, like, printing at a smaller scale. But if you want to print, like, really with the multi-material metallic compliant mechanisms, it's still still a long way to go. So I'll kind of, like, focus upon, like, some of the ways we have, like, at our lab, in some small way, try to overcome these kind of challenges. And hopefully that can be useful for, like, people to kind of move forward from that point. What we are going to talk about is a simple compliant mechanism. Those who are not really much aware about, like, the mechanism is very simple. Like, see, we want to produce motion based on the only the bending of some linkages. Okay, so if you apply some force on simple cantilever kind of a thing, you see that it deforms in the manner that is shown in the figure here. uh, there is a tilt in the block. At the same time, the block also moves in the direction that we don't want. Okay, we want the block exactly to move in a vertical straight line motion, but it is not happening here. So we put together some more kind of a linkages to do that, and then you see that, like, this block kind of now starts moving without tilt, but still there is some kind of a parasitic error. This is like called single parallelogram compliant mechanism. And then, like, you have this double parallelogram mechanism, for which, like, when you kind of apply force, there'll be a perfect straight line motion that is possible. Okay, so this is possible. You can see it happening here on the real mechanism, which is now happening here. Okay, so now this mechanism, if you see, is a monolithic construction. It is cut out of a single block by using EDM kind of a cutting or water jet machining and those processes. um, these are, like, expensive processes, and they typically will not be able to produce mechanisms which are third dimensional, okay, three-dimensional mechanisms. So there is some kind of a work that is needed to kind of, like, see how we can assemble these mechanisms together by using, like, uh, our traditional assembly ways. If you start applying, they typically tend to produce like mechanisms which are warped. Okay, even with the higher kind of a tolerances, these mechanisms would have some kind of warping that is shown. Okay, so the conventional ways, I mean to say, is when you locate two components with respect to each other, you need typically, like, two pins, or like, one pin and one half, like, oval kind of a location. Okay, but if you apply that to this kind of a mechanism, you will find that the mechanism gets warped. Okay, it's not really like a straight kind of a assembly. Okay, so we have come up with some kind of a guidelines which can help to kind of uh, locate these pin locations, how many pins and where the locations should be, such that the mechanism will come up when you assemble it, it will not be warped. Okay, so that is a, like, big advantage with this kind of a process. These are the guidelines which are for any n degree of freedom kind of a mechanism, or n link mechanism, I would say. Okay, so n link mechanism, how do you kind of get going with putting the pins and joints at some locations, very specific locations that are these guidelines they say. And when you do that, then you get a mechanism which is, like, completely warp free. Okay, so this is what is one of the important kind of a things. So these are one of the bottlenecks that we are facing way back in 2003 or 4, when we kind of started indulging into this area. And that's where, like, we started, like, looking at this in more details to kind of see, okay, how can we generalize this process and assemble any mechanism with n flexible links to come up with no warping in the thing whatsoever. And that's what now is achieved, and you can see that when it is done like that, with this kind of a, we have some kind of a process to do that based on this half joint design and things like that. So you can refer to the paper to kind of get into more details about. But when we do that, like, there are much lesser number of spins that are to be used in the process, and then, like, we get a mechanism which is not warped for the same kind of links and tolerances. Okay, so this is one of the important aspects. Now I'll kind of, like, switch and, like, first focus on, like, many different mechanisms or many different applications that we have developed based on such kind of mechanisms. And then I'll kind of, like, proceed for a little bit more delving into some kind of a mathematical aspects, so just to give you some glimpses about it, not get into too many details of the equations to bore you. Okay, so now we have this first application coming up with 3D micro printing. Okay, so we want to sprint at a micro scale, like, one micro, one spot size or one line's width is about 5 to 10 microns. That kind of a thing, if you want to print or produce, like, what you need is, like, the lens which will focus the laser beam that tight. Okay, and typically the focal lengths in that case are very small. Okay, so the conventional galvanoscanning methods would not work there. Okay, the area of scan in the conventional galvanoscanning methods for microprinting will be very, very small. Okay, so to overcome that challenge, we have come up with this innovative idea of scanning in the linear kind of a fashion, where we move mirror and lens together in the direction of laser beam to scan in one direction, and then further the same motion in the other direction to scan on the surface of the focal plane. Otherwise, in the conventional galvano scanning systems where you have SLA systems that are already commercial domain market, those are all scanning with a galvano scanning kind of a mirror, tilting mirrors, and they actually scan on the surface of a sphere. The focal spot is on the surface of the sphere, but the layer that you're scanning is actually planar. So there'll be defocusing happening, and like you'll lose the resolution, and you need to have some kind of a compensating mechanism to do that. That is what is overcome by this innovative way of scanning. Now we do this scanning by using our compliant mechanisms like this double parallelogram compliant mechanism, and build a complete system. And then when we test this system, you can see that because there is no friction in the system, there is no backlash in the system, we are able to kind of get to the accuracies of up to 100 nanometers kind of accuracy. Very, very highly accurate kind of a, this is in the closed loop position kind of a control accuracy. And we are able to kind of now do this very routinely over large area of a scan or large deformation of these linkages. And the entire system then looks like this. Okay, so this is kind of capturing somewhat like the entire system built using this kind of compliant mechanisms, and it is doing like the 3D printing operation here. You can see here the other beam is coming from the bottom side, and it is scanning in one direction, and then there is entire other compliant mechanisms here which is scanning in the other direction, second direction. Okay, and the scanning would proceed like this. So as a laser beam is scanning, like your beam is switched on and off at certain points to kind of get whatever geometry that you want to print. In this case, this hexagonal kind of a mesh, and you can see that meshes start developing here. Okay, so this scan, when it is complete, like one layer is completed, then you actually kind of get into and like move the Z stage in the up and down kind of a motion, and you can see that motion happening here for this Z stage. And then once that is there, like second layer is ready with the Z stage moving, then you get like next sprint and so on and so forth, and you can build like many such kind of a components now. Okay, so this is like a really micro printing kind of application. You can build like very interesting kind of components and mechanisms by this kind of a 3D printing kind of a way. Okay, so we move on now to the next application. So I'll talk about this a little later. This application with this compliant mechanisms which are in a resonant displacement amplification kind of a mode. Okay, so see, we already have mechanisms which are having these compliant linkages. Okay, so it is very easy to get it into a resonant kind of a mode of operation. Okay, when you get like say for example like this double parallelogram mechanism, the intermediate stage when it is actuated by a magnetic actuator here at a frequency which is close to the frequency of inner two beams and the mass, then this will kind of oscillate at a frequency which is close to resonance, and then it is amplified displacement. Okay, so small like motion of this magnetic actuator would actually translate into large like 3 or 4 times large motion of this resonant stage here. Okay, so now this we can like put it at an advantage to kind of have in the mechatronic system smaller size actuator, smaller capacity actuator, and then like it's like a and cause a motion which is much larger. It's like a pendulum of a pendulum clock. Okay, where it keeps on oscillating, and you just need a energy only to kind of like the maintain the oscillations. Okay, you give a spring once, and then it keeps on oscillating forever or like long time. So this is the kind of idea that is used to kind of reduce the power consumption in the conventional kind of a systems to do the 3D printing kind of operation. Okay, and along way, like you need to kind of optimize the parasitic error, because now if these linkages would have been of the same length, for example, they would cause now additional parasitic errors. Okay, it will not compensate completely, and because of that, we need to have some kind of optimization of these linkages to be done. Okay, that's what we have done, and maintain like make sure that okay this motion of this resonance stage is still a straight line motion. Okay, and with that we get this kind of a video of the motion happening. So you can see here there's a voice coil stage here, and then like much larger motions happens here, and now we use this for doing this 3D printing business. Okay, so we term this printer as Spanda 1. Spanda being like, the meaning, the pulse of creation. Okay, so so these are like, some of the components that are printed out of this printer, and you can see there are pretty highly accurate kind of a component that getting printed. Okay. Now we move on to the next application, which is which we term as bulk lithography. Okay, this is a term that we have coined in the literature for the first time, and like, it is a very interesting process of like, doing the fabrication by changing the intensity of the laser beam along the way when it scans. So, for example, if you scan and while scanning you change the intensity, you can get a shape which is fabricated having like, the third dimensional some kind of a formation that can be happening in the third dimension. And this is what we use to like, do a lot of kind of structures which are relatively small in height, but having like, free form kind of a surfaces. Okay, those kind of structures are very easy to form by this kind of a principle. And they are useful for many kind of applications, including this microneedle fabrication or some of the biosensors or diaphragms and things like that. Okay, so some of the microfluidic also can be done with this kind of process, which we are exploring right now. We have gone like, lot more details into this laser photopolymer interaction. Okay, model from like fundamental physics of Maxwell's equations, and we actually kind of considered along the way the the change in the refractive index of the resin material, which is based on the intensity of the laser light it is exposed to. And because of that, like, so when the laser light shines here, like a small voxel will be forming. That voxel will itself act as a lens, and it scatters the beams in a way of depending upon the refractive index change. And then next voxel will be forming, and this so on and so forth. Like, you get complete kind of a evolution, and you can see that this evolution has very specific kind of a shape that is happening here, which is very interesting to kind of know that okay, there's a bulge and like, some kind of a shape that is happening, and we are kind of very curious about that. And we model entire of this phenomena from first principle physics, along with like, considering the radical diffusion processes. And then like, it was predicted that okay, what kind of shapes would be formed, and they are matched actually with the experimental kind of shapes, to kind of say that okay, we are able to now predict like, what kind of shapes will be formed when single beam of light is shine on the photopolymer resin for some kind of a duration of time. In this case, it is like, zero point 0.5 seconds, and many different kind of forms and shapes will be formed based on the different parameters. They are useful for like, for getting the micro needle application going on this. Okay, so that is one of the kind of other applications that we will be developing. Um, these are some of the snapshots of like these 3D printed components based on this technology. You can see that there is a smooth surface variations here, or smooth surfaces, instead of like, the stair stepping effect that you'd see otherwise in a layered kind of a processes. Okay, so so these are the like a needle kind of a structure that will be formed. You can see that 20 micron scale, they are really sharp, and that can be used for the micro needle kind of application, where you have a uh, when you say you have mosquito bite, you hardly notice some kind of a pain, but when the doctor gives injection, it's like, quite painful. So you can have now this micro needle based hundreds of like needles coming and sitting on your skin to give you drug delivery. So that will be very useful for like, drug delivery, especially when in the rural areas where we do not have the medical support or nurses to kind of give injection. These microneedles would be very helpful to kind of carry out this drug delivery kind of a application. Okay, so next one is this micro milling application. So we said okay, now we are able to kind of do micro printing, we can do micro milling also, and we developed this entire technology for micro milling kind of a purposes, again with the similar kind of a compliant mechanism stages here. And it was actually licensed to one of the industries called Strategy Automation in Bangalore, and they displayed this product in this Imtex exhibition and won an award there. This technology is working in this video you can see here. so this stage is moving, and then the spindle, when it drives. See, this is like a soft. See, I must say here that for machining purpose, this is very useful, because compliant mechanism based things typically would deform when the higher tool forces will come, and it will save the tool from damage. Okay, so that is another advantage of these compliant stages used in the machining operation, where, like, your tool will be saved from damage, because the tool forces will deform, like, the mechanism more, than then, like, you'll be saved from tool damage. Okay, then these are some of the kind of components which are machined. You can see at 2 mm scale, like, you see very high precision machining can be possible with this micromilling processes. Now, this is other application we developed for one of the industries, where they wanted to kind of develop a tool touch sensing, and based on the tool touch sensing, you need to kind of, like, move the tool at certain place and give some kind of a cut for the encoder disc to be mounted on some kind of a mount. Okay, which is very high precision kind of application. They wanted this to happen within, like, 5 to 10 microns kind of accuracy. So this touch detection should happen in that accuracy, and for that we employed this compliant mechanism. And then with that touch detection, now this complete operation is carried out. So this entire kind of a application was developed in house for this company, and it handed over to them. So this tool now is going to touch down, and, like, it touches this kind of a sensor here, and it comes up, and, like, then gives a cut on this disc in a accurate kind of a fashion. Okay, so this is now coming up, and now, like, getting the operation of cutting initiated. Okay, so you can see here the cutting is happening now. Okay, yeah. So once these cuts are done, then, like, the encoder disc can be very easily mounted on the surface, and the compliant mechanism is actually holding this tool here. Okay, it's simple double paragram compliant mechanism, and again, uh, we have this advantage of, like, being guided by compliant mechanism. The tool will have inherent kind of a uh, flexibility to kind of happen to make sure that, it does not give very high kind of a cutting forces will not come on the damage side for the component. Okay. Uh, so this is transfer technology, and, like, this is already probably in their operation for manufacturing these encoders for industrial applications. Okay, so now this is another kind of a technology that we have built on, like, this is highly compliant kind of a mechanism here, which is similar to our double parallelogram compliant, but this is the flexibility is too high here, like, the deformation you can see is too much, and this is done for the purpose that, you can sense very small forces because of this high flexibility. Okay, so we can do that for flexible electronics testing purposes. Okay, so we actually did that for one of the PhD thesis from IT Bombay, for like, developing a flexible electronics and testing it for their strength kind of purposes. Okay, so this is a very special kind of a UTM kind of a thing that we have developed based on compliant mechanisms, and also it is tested for one of the shape memory alloys kind of wires to test. Okay, so this solution is not currently there in market, but then it can be now used for, like, it's kind of technology ready for commercialization, I would say. So here there is this kind of a shape memory alloy wire, and it is given some kind of a current through these two blue wires that you can see up around, and at the same time you can kind of use this compliant mechanism to kind of give the known force on the wire. Okay, and see or measure the force when you are passing current through the wire and things like that. Okay, so this is already characterized for one of the companies actually, and I would say this technology is ready for, like, any kind of further kind of usage. So see, this some of these kind of industrial usages of these mechanisms, it was also, like, Professor Belgaonkar's forte actually. He developed, like, not only theory but also, like, a lot of industrial kind of usages for some kind of mechanisms he developed in his era. So this is like a compliant mechanism for linear scanning probe. So these are like three XYZ kind of translation stages put together in one kind of a unit. to measure the stylus deformation for CMM kind of a probe application. Okay, so this probe will be more accurate than what is current technology in the Renishaw kind of CMM probes. Okay, so all these three axes are motion with like roughly about 5 mm motion is allowed for this analog scanning. So that means when this probe some goes around some unit up to 5 mm kind of a deformation with the accuracy of about uh, 25 nanometer uh, can be detected. Okay. Now we are talking about some different kind of a compliant mechanism for angular lifting, okay, of one slide with respect to other side, for a very interesting process that very simple but very kind of elegant and interesting process of fabrication of this control geometry, fractal or array geometry kind of structures by shaping the fluids. Okay, so I'll tell you what this process is about first. So you have this top and bottom plate like a glass, and this small fluid drop like Fevicol or some kind of a viscous fluid, and you compress it, and you form a complete film out of that. Okay, when you compress, now imagine if you kind of get the slides back again, separate them from each other again. This film is not going to go back as a drop because it's a viscous fluid. Okay, so what happens actually is this circular interface is punctured at many places, and then from that punctured interface the air starts getting into the film, and then when you kind of this air progresses further as you kind of start separating the place, and when you separate them completely, some kind of fractal geometry structures are left on the surface. Okay, so that is what is a basic process that happens. And to happen make it happen in a way, in a controlled fashion, we have this kind of a small compliant kind of a link attached to this plate, so that when you kind of cause a motion here based on this voice coil kind of a movement here, this these two slides will um, you know separate angularly in a way that you have a fixed center of motion. Okay, although there is no hinge at that point, it's like a remote fixed center of motion. Okay, so it's like a compliant RCM kind of a mechanism. Okay, that is what is we are looking at here. So you can see this video how things happen. For example, you watch this thing in the circle, you can see this ball that is coming and pressing something, some extension of this plate, and this plate is going to kind of move down now, and guided by this kind of a compliant mechanism. Okay, so this is a compliant link which is guiding this plate, and the rotation is going to happen about the point roughly somewhere here. Okay, so as you can see, it starts now moving. Oh, this video is not playing yet. Okay, yeah. So the motion happens about this hinge point, and the hinge point doesn't move from its location. There is no physical kind of a constraint for that point to move, but because of this kind of a compliant link guidance, it is not moving. This point is not moving, and there is a pure rotation about this point for this plate that is happening. And now we use it for many different kind of applications. We have created this as a angularly lifting kind of a, we call it Helleshaw cell, when the two plates are kind of moved angularly with respect to each other. And in this case, there are these compliant mechanisms here again, three-dimensional kind of a mechanism to kind of move this plate parallel to each other on the large scale. This is like about 1 feet kind of a circle here, on which this process can happen also. And we can create many different kind of interesting geometries. The important part is that the compliant mechanisms usages here is for the purpose of this ultra low speed. See, if you imagine, if you want to have a very continuous motion with a speed of about 1 to 10 micron per second, it's very difficult to achieve, or infeasible to achieve in some places where you have two components rubbing against each other. You have some kind of a guide, and there is some even small friction will not allow you to kind of move at such a kind of a low speeds. Okay, so that's where this compliant mechanism do a magic here. Okay, with this because of these compliant mechanisms, even for this large kind of a system, we are able to move the 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 plates with the speeds of so slow, and those speeds are needed for the some of the structure to evolve in a very kind of a controlled fashion. Okay, so that's what is a use of compliant mechanisms in this particular kind of a case. Okay, so here you can see the entire process happening in some kind of a video fashion. Okay, so this is one of the setups that I was developed in house for the process. And then the process begins with creating some kind of these anisotropies on the surface of uh, these cell plates, which are basically acrylic material, and we drill these kind of holes, and then we put a fluid drop as we saw. And now this is now will happen in a machine, or like our setup that has been developed. And this calculated amount of fluid is done to kind of make sure that when you press the two plates together, like you get a particular kind of a size of the circle happening there. Okay, so you see the drop here, and then like now this plate now will get moved, and you can do the fluid stretching by you can see this plate is touching now, and like the fluid drop is kind of expanded. Okay, in the top view it happens something of this sort. Okay, and then like now you do some kind of a fast process, then this will not happen. The respect, the holes will not be respected in this case. But now when you do very slow kind of a process, that is what is empowered by the compliant mechanisms, then like these the fingers or air will pass through these holes that are drilled, and you get now this completely controlled kind of a structure pattern here. Okay, so you can see now many different kind of patterns can be coming up with this process. Okay, so I can see you can see here different patterns can come up, including this kind of array geometry, hexagonal cells, and many different kind. This is like a first level control of the end branches, then square kind of a geometry, and these are now we are like exploring a lot of different kind of usages for these patterns. Okay, they are very helpful in biological kind of application, because all our biological systems have like some kind of a fractal geometry kind of structures. Okay, you see your respiratory system, for example, you have veins which are going and splitting into multiple, and whenever the oxygen exchange happens, they are very tiny there, and then they come back in a similar kind of a fashion to have this application done. And nature has done this for a reason. The with this kind of a geometry, you need hardly any energy, or you need much lesser energy to kind of drive these applications. For the same efficacy, you need very less energy. So that's where now we are moving towards getting these many different applications developed over these kind of fabrications. Okay, then the next application is about this remote center motion kind of a compliant mechanism. You can see it here, where we arrange the linkages in this kind of a tilted fashion to make sure the motion happens with the remote center of motion, and you can see that happening in this video here. So this is a compliant mechanism that is developed for remote center of motion, and remote center is matched to the end point of this needle. Okay, so you can see there is no hinge, physical hinge there, but this remote center kind of motion happens about that point, and this kind of is very useful for very high precision eye surgery kind of a robot. Okay, where you have this point matching the hole in the sclera that is made for moving the tool inside the eye. Okay, so that will be one of the other applications. Then we have developed some kind of a digital torque sensor without using strain gauges, but you have this kind of a linkages arranged in a fashion to kind of get you. These are two encoders. There is an encoder which is measuring the relative displacement between these two disks here, and that kind of gives you the sense of the torque in the system. And this is very precise encoders. If you put you get very high accuracy digital output for the torque sensor. Okay, where there is a problem of analog kind of output with the noise coming, this is a very useful kind of a sensor to kind of go. And this is demonstrated in some harmonic drive application in our lab. Okay, this is a eye surgery robot kind of a tool that is developed now. We are using this torque sensors here to measure the the forces that the surgeon. So this is a surgical tool that will be shared by the robot and the surgeon together, and any forces that will be sensed by the torque sensor, and then the operation cooperative surgery can happen in that kind of a way. This is another interesting application that we are currently developing, where you have very highly flexible linkage, like this is inspired from like leech like action, where this robot is moving with these linkages, which are highly flexible linkages to kind of give you this motion. Okay. Uh, then another application is of the harmonic drive. Okay. And this harmonic drives are like these flexible gear transmission systems, where we have the motions happening because of flexing of this flex spline or the gear, and because of that you get very high gear reduction ratio. So this has been developing, this has been there in the literature in the world otherwise, but in India there are very hardly any companies who are actually developing their own harmonic drives. So we have now this technology developed in house with the support from DRDO project, and now this is available for anybody to kind of use. We specify, you specify the specifications, and we'll be able to kind of generate our own kind of a harmonic drive, which is have entire kinematics of the gear tooth profile is worked out. We have a code now written to kind of generate this kind of a tooth profile, and also we have done FE analysis to kind of validate the strength of these drives. Okay, and we have this test setup that is developed to kind of test these harmonic drives to with our kind of a torque sensor here, which is compliant mechanism based torque sensor here, to do the complete testing of the harmonic drive to predict what is the efficiency that it will give for a given tooth profile. Okay. Now let us kind of switch the gear and let us get into a little bit more of a we have some time, right? Okay, so in dynamics and controls of some of these kind of systems. So we start with a simple system with a flexible in a horizontal plane, which is already solved problem in the literature. We don't need to worry about this is one of our course design of mechatronics systems kind of a course project, where you can see that very nicely this very highly flexible beam is getting controlled. So this horizontal plane, this problem is well addressed and well solved. But when it comes to vertical plane, okay, you have this ultra flexibility in the system, where the beam, the mass is more than the buckling load that the beam can take. Okay, so this is like a post buckled kind of a system, and this is like a post buckled uh, ultra flexible pendulum on a cart kind of a system. Okay, and for this system, if you see its dynamics is very interesting. Now this system is stationary here, cart is stationary, but you just kind of set it in initial kind of a condition motion. What happens is it oscillates between the two equilibria which are on both the sides, and then interestingly it oscillates only it gets into only one side oscillate, because it now the energy is are such that you have two potential energy well, one on this side and one on this side, and the middle kind of a position is unstable. Okay, it's a unstable equilibria. You have two equilibria stable on two sides and one unstable equilibria. Okay, so now control of such system, dynamics of such system is a very challenging kind of a problem here. Okay, so the system will kind of eventually stabilize into this kind of a side equilibria here. Okay, so now if you oscillate the system with a sinusoidal kind of oscillations, this is what happens here, and you can see here a point kind of map for the system, where you have the points all over. Okay, so this is quite unpredictable, that okay, it will oscillate on one side or the other side, or when it will switch from one side to other side. Okay, so this is a kind of a some kind of a chaotic regime of oscillation for this system. And to characterize that, now we have system modeling done here by using some kind of a assumed modes kind of a method. So we have done the static modeling also, and we have done some dynamic modeling also. So here we first need to kind of do some static analysis to kind of validate this equilibria. Okay, so idea is key ideas for this modeling is you have this large deformation that are to be considered in the system. Specifically, if you see typical um, Euler Lagrange, Eulerian beam, you have the small deformation assumptions. That means when the beam deforms, its length is kind of somewhat preserved. Okay, there is no the actually the beam length is like no finite. I mean the or fixed, but in Eulerian kind of a Euler beam, like no you don't respect that. Okay, because you assume the small deformations. But when you have large deformations, you actually need to kind of see that the beam length is preserved. Okay, even if the beam doesn't have like you assume that beam doesn't extend or like compress because it's like very stiff in that direction. It's like more like a bending kind of a system. So then this lowering of the potential energy is to be considered. Okay, and that's what is responsible to kind of give you this two side equilibria. So that is what is one important kind of a consideration that needs to happen for these systems to kind of get modeled rightly in the with these kind of elastic deformations. And so for that purpose, we do this like a length constraint we apply on the system. So then it gets into new formulation called constraint Lagrangian formulation. Okay, so 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 this is what will give us like this equilibrium kind of a configuration for the two equilibria to happen. Okay, so we now plug in this assumed modes method to assume the deformation to be a time and separable function of time and space. Okay, and then this is where like these model functions are like standard beam model with the boundary conditions, respected boundary conditions are applied, and you get this kind of a mode shapes. Okay, and this q becomes your generalized coordinate here. So in addition to this, we have this length constraint that is imposed on the system. Okay, the total beam length from what was the initial length was say suppose L, that remains kind of L after even after bending, and that's what is given by this equation. Okay, now with this we get into this constraint Lagrangian formulation to do the analysis. Okay, so this Lagrange of the system is based on kinetic energy and potential energy. Specifically, now you can see that the beam energy is here, and the stored elastic energy is here, and then this is the energy based on the lowering of the mass, this mass here. Okay, so we introduce this variable called xc, which is like the deformed length of the deformed like along the length direction the deform in the beam deforms, that is a variable. So now this xc is like a new variable that is coming in picture, and we have like this length constraint based on this xc variable also coming in picture. Okay, so 0 to xc, like you have this length constraint coming in, and then you do this constraint Lagrangian formulation with this Lagrange multiplier lambda here, and generate the equations of dynamics. Okay, so these are the equations of dynamics with lambda, and eventually you can eliminate lambda from these equations by some kind of a mathematical manipulation, and these kind of a forms will be now useful for dynamic analysis and control purposes. So one can also do this kind of analysis by using FE. Okay, but the aim here is to kind of like develop models, develop insights into dynamics, and further they should be amenable to control development. Okay, so that if he gives you so many kind of like multivariable kind of models which are not really amenable to kind of like the nonlinear control kind of a method. So this gives like very simple insights into system with less number of generalized coordinates. Okay, so with this form, like these are just a different constant in the system, and you can see the dependency of these constants over the space variables. Okay. Um, so with elimination of lambda and introduction some damping in the system, like we get some kind of interesting insights into the system when we plug in for the dynamic like equilibrium for this dynamical system. Okay, and then this is an equilibrium condition for this system. With that, you can see this equilibrium kind of a solution comes out to be like this, as shown in the red kind of a line, and then it is compared with elastica theory, where you it's like a um, where you do not have any like no assumptions for the system. So that's kind of considered as a some kind of a gold standard for comparison purposes. Okay, and with multiple modes also we can now, so interestingly, for this system, when the p by p critical or the mass is more than the second buckling load. Okay, second mode buckling load, then you get now additional kind of a stable positions for the system. Okay, so this is like one position. So the number of equilibria would start increasing as you increase the mass is what happens in this system, and that's what is captured in this kind of a figure here. So up to kind of like the first kind of a p by p critical first like load, it has only this like so at this point, like so below that load you have no side equilibria. Okay, so system is not buckled. Okay, when it buckles for the first load, we have equilibrium on one side and other side, and central equilibrium is unstable. Okay, that's what happens at this point. Okay, p by p critical is equal to 1. And when this ratio increases further at some point like 9, like you have additional split that is happening in here. Okay, so this is a bifurcation that is happening to kind of get more and more equilibria in place for this system. Okay, um, so you can see that here if you kind of just take one slide back. Oh, it's not working for the back button. Anyway, like it will have beyond 9, it will have 5 equilibria. Okay, before 9 it will have 3 equilibria, and before 1 it will have only single equilibrium. And this is how like the phase plots will typically evolve for the video that you saw in the last slides. And this is how like the evolution of now theoretically also or numerically also the evolution of chaos happens as you start changing the frequency. Like you have first cluster splitting into two clusters here, and then like the two clusters split into complete like this kind of a chaotic kind of a cluster. And then further like you start increasing, and again you start seeing these two clusters again coming together, and then like the chaos kind of vanishes from the system. Okay, so this is about like the theoretically and experimentally like looking like the point grid maps. Okay. Now, control development for this system, there are multiple ways we have tried. We have used like I'm presenting only this energy shaping kind of a way which we have done in collaboration with Professor Romeo Ortega's group in Central Super Lake at that time. And here the idea is you propose some kind of a desired energy functions. Okay, where you want like so the control problem here is like this is this system on the cart, and you move the cart in such a way that you want to stabilize the central unstable equilibrium. Okay, how do you kind of do that? Okay, that is a main kind of a control problem here, and at the same time you want the cart also to reach some kind of a desired position. Okay, so these are kind of two control objectives. We have only one actuation here. Okay, and that's where this energy shaping kind of a ways of doing things come in picture. And so here uh, the step one is like the partial feedback. The system is partial feedback linearized, and you get like this system in this form where like you basically you use this z double dot or like the cart acceleration as an input to the system, and then like you reduce the system into this kind of a form, and now this system is much easier to work with to do the energy shaping kind of a so on that you identify the passive outputs. These are identified here, actuated and unactuated part of the passive output, and then like you develop the control over the combination of the passive outputs. Okay, some linear combination of the passive outputs is taken, and you kind of do some PID kind of a control over the linear combination of these passive outputs. Okay, and that's what like is done um, to kind of prove that then you define this energy, new energy of the system to have a so this energy is defined is coming up in such a way that the central equilibrium here is having the least energy. Okay, so if you see in the form of this particular definition of energy, the energy will be least for this central equilibrium here and higher for the other side of the beam. Okay, so that's how like you new definition of energy will happen, and then you propose control law accordingly, and then you have this control happening for the system. This is a simulation result, and both like the card position is also driven to some kind of a zero, and tip mass is stabilized at the zero. Okay, so you can see the control working in this video. So these are some kind of system parameters that are used for control purposes. This is a simulation result you can see. So the cart is moved to kind of make first the the system stabilize in the vertical position, and then it is brought to the zero. Okay, so this typically happens in a simulation now, and same thing now you can see in the experiments here. Okay, so these are experimental results for the same case. So you start and so the sensor feedback is at the bottom here. We have a strain gauges, and then the strain gauges are this amplifier for the strain gauge, and then that input is given to the system to get a feedback, and then you develop this control algorithm. And this just is just an arm to kind of save the system when something goes wrong. Okay, so don't worry about this part here, just to kind of absorb the shocks if at all something is going wrong. Okay, so this is how the system is getting controlled. And then now if you see, you want to kind of give some disturbance and check that that is happening here. Okay, so somewhat the system is kind of able to reject the disturbance and get stabilized at the position. Okay. Um, Next is this ultra flexible beam on the hub kind of a system. So I'll quickly finish with a couple of slides now. So this is the currently ongoing work in our lab where we want to now create this kind of a system with same kind of a flexible pendulum, but now on the hub. Okay, instead of on a cart. Okay, and this is much difficult kind of a problem, because now in this dependence of this multiple equilibria that I was talking about will be also on this theta. Okay, so the state dependent or dependence on multiple equilibria, I think we are reporting for the first time in this case. Okay, so you can see these are multiple equilibria that are appearing as in the case of our previous system as well. But now as you change this hub angle, the equilibria would change, and they change in the fashion as shown in here. Okay, so this is a plot of the equilibrium kind of position of the this position of the tip mass in y direction particularly. And as the hub angle changes, you can see when the zero hub angle, you have these three equilibria. They continue to happen till some kind of a hub angle 1.5 2. At 2, there beyond 2 there is suddenly only one equilibria would exist. Okay, so all two other two equilibria vanish, and this is how the picture happens here on the actual simulated kind of equilibrium positions. So you change the hub angle more, the this equilibrium actually shifts here. You can see that this is a hub angle position 1.5 degree here. Then beyond 2.5 or beyond 2 degree, you can see that only one equilibrium would exist. This is that these two positions are, one is elastica solution, and other is assumed modes method kind of a solution. So typically assumed modes method will have only one kind of a mode assumed, so the solution is stiffer than the actual system and elastica solution. Okay, and then this is last slide to kind of show you, this is some kind of open problem which was done as a part of this one of the course that I taught recently. Some students took up this system to kind of do some kind of experimental fabrication here for design of mechatronic systems kind of a course. Okay, so this is their course project final video. But this is very interesting system now we want to kind of analyze for. So you can see that there is a single circular kind of a link, circular cross section kind of a link, and it has a mass at the top, and that is like a 3D flexible pendulum kind of a system. That mass is moving all in space, three-dimensional space. Okay, so this is like a kind of open problem, I would say so far. I mean, we have to look at its modeling and control aspects further. If anyone of you interested will be happy to kind of collaborate and see some developments in that direction. Okay, so with that I conclude my talk, and thank you very much for your presence, attention throughout this long talk. And I'll be happy to take any questions and any welcome to any collaborations as well. Thank you very much. must acknowledge here, I forgot that. This all the grants that we received, and also like the contribution from a lot of our students who have relentlessly done a lot of work and achieved any very interesting kind of a systems.
Thank you, Professor Gandhi, for that very insightful talk. We have time for maybe a couple of quick questions from the audience. I'll pick it up.
Thank you very much, Professor Gandhi, for your excellent talk. I was wondering, you showed compliant mechanisms that were loaded by the machining forces.
Right.
That is quite challenging. I was wondering if you took special precautions to carry those loads and not get into resonance and those kind of things.
Right. Yeah, it's very. So see, the thing is that the loadings are coming in the kind of parasitic directions where we want. So where we make this the compliant mechanism very stiff in that direction. Okay, so those loads can be the cutting force loads that can be taken, vertical loads. Okay, so the system is designed to be stiff in that direction, and that stiffness is like very high in that direction. Only in the direction of motion, direction of degree of freedom, you have a lesser stiffness. Okay, and so far, as far as the resonance is concerned, because this machining is at very high speed, and typical frequencies of the first model frequency of the mechanism is like low. We didn't see, I mean, we didn't observe resonance related kind of a problems in the system so far. But maybe like we have to kind of particularly match exactly some resonance frequency or higher harmonics and then see its effects. But we have not done that so far. Yeah. Yeah.
What kind of practical studies we can use it for?
The 3D pendulum system.
3D
Okay,
pendulum.
so see, all these nowadays people are talking about these soft robotic systems, like multiple such pendulums connected together by some with some actuators in between could be a system for or some kind of a robotic application. That's what I'm envisaging.
Okay. So yeah, very nice presentation. So I was just wondering, have you thought of applying on some flexible wings? Like we have some aircrafts where
Okay.
we consider those are usually very rigid wings, but
Yeah. So far, no. Sorry, I've not really thought about like using some of these to aircraft wing kind of structures. But maybe if there is interest, maybe future. Yeah.
yeah, very nice
Yeah.
work.
Yeah. Thank you.
Thank you.
Okay, in the interest of time, that would be the last question. And with that, we are at the end of the memorial lecture. As a token of appreciation, AMM would like to present Professor Gandhi with a memento and honorarium. I'd like to invite Professor Ghoshal to present these to Professor Gandhi. Yeah, yeah. Yeah, there's a video I'm going to play here. I'll play a video here. There's a video I'm going to play. So the memento presented to Professor Gandhi is a dynamic one, and there's a brief video which explains what it does. It's coming up in just a sec.
Mechanics, we know that the components of a rigid body. Professor Bindu Madhav Belgaonkar, a visionary mechanical engineer, was instrumental in connecting AMM with IFTAM. The same is captured in Professor Bindu Madhav Belgaonkar, a visionary mechanical engineer, was instrumental in connecting AMM with IFTOM. The same is captured in this memento. This memento is inspired by a spatial RR manipulator with zero workspace. In mechanics, we know that the components of a rigid body that lie along the axis of rotation do not change their position in space. Now, if we consider multiple axes of rotation and make them all intersect at a common point, that point remains fixed in space even as there is rotation about all axes. From a mathematical perspective, such an arrangement corresponds to a solution lying in the null space of the combined rotation matrix of the spatial RRR manipulator. This forms the underlying principle of this memento. The first rigid member is labeled IFTOM while the second is AMM. The third member is attached to the ball which stays at the same location. The ball symbolizes Professor Balgaonkar, the invariant figure, the common point and the reason for bringing IFTOM and AMM together. As shown in the illustration, the ball lies along the axis of all the revolute joints. Consequently, no matter which joint is actuated, the ball remains stationary in space. These are the images of the memento, and this is the video of memento in action.
Now, I would like to invite Dr. Himabindu from IIT's MAE department to present a Cheerial mask as a token of gratitude to the speaker from the organizing committee of this year's conference. Yeah, yeah, we'll put it in the box. Please join us for a photograph. Sifan, you should. For a photograph. That's fine. I've been captured enough in pictures. Nothing. Yeah. So we'll box. Yeah. We have one. Can you put this in there? So we'll meet here again for the invited talk in about 15 minutes after a short tea break. There's tea waiting outside.
Yes, sir.
Welcome back. If you've ever wondered how we might apply the principles of mechanisms and machines at the scale of a single cell to reveal its mechanical behavior, its elasticity and isotropy, and response to complex deformation, today, Dr. Srinath Balakrishnan will offer insights into a suite of compliant micromechanisms that enable manipulation of individual cells. Please welcome onto the stage Dr. Srinath Balakrishnan. Dr. Balakrishnan obtained his BTech and MTech degrees in mechanical engineering from NIT Calicut and Virginia Tech, respectively. In between these degrees, he worked with Larson and Toubro for 2 years. Later, he did a PhD in bioengineering from Indian Institute of Science at Bangalore, and subsequently joined the School of Mechanical Sciences at IIT Goa. His research lab at IIT Goa, BIMODE, Design and Modeling for Biology, is working on developing tools and methods at the intersection of biology and mechanical engineering. Professor, the stage is yours.
Okay. Thank you for. I would like to thank all the organizers of this conference for inviting me and giving me such a nice prime slot in the conference, especially of the first memorial lecture. So my talk is entitled. Okay, compliant mechanisms for manipulation of single cells and single celled organisms. So before I start, I would like to give a brief motivation on why this is such an important topic. So from most of our childhood, we would remember biology as some kind of chemistry in action. So you had a bag, which is, let's say we call it a cell, and there is a bag, and then inside that bag you have a bunch of chemicals which are interacting, and that's how life happens. But that is not the accurate picture of life, because what we have realized, starting from, let's say, early 20th century and intensified over the late 20th century, is that the mechanical forces, mechanical properties of bodies uh, do matter. To give a simple example which anybody can relate to is, when you do exercise, what you're essentially doing is you are putting forces on different parts of your body, but then that actually improves your muscle strength, your overall health. So something is being done by the forces. At the other end of the spectrum, if you want to talk about diseases, something which we all hear about quite a lot is cancer, and the real danger in cancer is what is known as metastasis, where the cancer cells move from their primary location where it is to secondary locations. So for that to happen, the cells have to actually migrate through the body. It has to enter the bloodstream, and then it has to go to other locations. So the entire process is actually mechanically very intensive, because the blood vessels are lined with cells which do not leave a lot of gap. So the cells have to literally squeeze through. So what people have found out is that the cells, actually the cancer cells which actually metastasize and create lot of fatality, are the ones which actually become more compliant or less stiff. So over the past 2-3 decades, people have realized that the mechanical properties of cells are actually very important. And in response to that, there have been several methods that have been created to calculate the mechanical properties of cells. So I'm just giving you a few of these. People would be knowing about atomic force microscopy, which is essentially a cantilever which is indenting a cell. You have something called micropipette aspiration, where you have a small um, tube which is sucking a cell, and you calculate how much the cell is going inside with respect to suction pressure. You have optical stretcher, where you can have beads which can the beads which are trapped by laser beams, and the beads are manipulated, and these beads are connected to cell. So then you can stretch a cell. You can have what is known as a microplate stretcher, where you have two plates and the cell is attached in between, and if you move the plates, you can stretch a cell. You have something called as magnetic twisting cytometry, where you take a small bead, you attach it to a cell, and now you twist the bead using magnetic field, and that's how you can deform a cell. Another popular technique is what is known as substrate stretching, where you take a substrate, a flexible substrate, you culture cells on them, and then you stretch the substrate. So these are some of the popular techniques. There might be another like half a dozen or so, but these are some of the most popular techniques. What you would appreciate if you look at these is that um, each of them does a manipulation in a particular way. and each of them, if you think of it, they are by itself, they are quite expensive, because I don't think you can get an atomic force microscope for less than 1 crore rupees, and actually probably a lot more than that, and similar for most of these. So for each manipulation you would have to invest a lot of money, and then each of them requires very intricate specialization of the people who are actually using the system. It's not easy to work, I mean, like, to use this, so it takes a lot of training. So the result of it has been that if you look at any research paper, you would see only one kind of manipulation. So let's say somebody is working on mechanical property of cells, they would work only with AFM, or somebody would work only with optical stretcher. So you would not see any research, very few research papers with multiple techniques. And as mechanical engineers, we know cell is a very complex system. So you would actually require multiple parameters to really characterize a cell. So now, how do we solve this problem? How can we solve this problem of doing multiple manipulations in a single device? So we think the solution for that is using compliant mechanisms. So using a compliant mechanism, one of the larger aims of my lab is to create a lab on a chip where you can integrate multiple types of manipulation into one chip. So this uniaxial testing mechanism, this is something that I had developed during my PhD with Professor Anand Suresh, who is sitting here at IISc, and we are now developed a biaxial stretching system, and we are also working towards two other devices which can be used for twisting a cell and shearing a cell. So I'll just show you the process of how we developed and what are the designs and etc. And we'll also extend this to other systems, not just cells, to other organisms as well, microorganisms as well. So let's say, for example, biaxial stretching, a characteristic way would be to actually convert into a mechanism design problem. So let's say you have a design problem where what you want is inside a domain, you want to have one input port where you want to put one force, and that should actually result in 4 points moving outward. So if you can solve this problem using a mechanism design approach, then you essentially have a biaxial stretcher. So this is a design that we came up with. It is essentially uh, an auxetic structure which is actually driven by a gripper, and it's actually goes the other way. So you can see that when I push here, these four will move outward, and by changing the angles of these auxetic structure, you can actually get multiple stretch ratios. You can get 1:1, 2:1, whatever stretch ratio you want. And this structure, since there are no joints like all compliant mechanisms are, you can easily, I mean, you can microfabricate them. I would not say easily, but you can microfabricate that, and then you can see this is the kind of the same mechanism, where if you put a input here, this is a single cell which is uh, on the mechanism, and that is being stretched in two directions. Now, there are a couple of advantages of using compliant mechanisms for such a device. So one of the advantages that you can probably see from this video is that the mechanism, this is made out of a material called SU8, which is transparent. And then, so you can do very high content imaging, high magnification imaging during this manipulation. So you can get a lot more information from the cells by imaging them. And another thing which is probably obvious to many people who work on compliant mechanism is that because the force transmission is happening through deformation, what is the force expressed? What is the force? The stretching force that is causing the cell to stretch, that can be computed from the mechanism deformation, and this can be done. So you can take this auxetic structure, you can break it into a quarter structure, you can analyze it using beam theory, and then you can come up with a relationship between what is the stretching force and the deformation of the mechanism. So we have developed those formulas, and then we have verified it at the macro scale. So here you can see some experiments. These are done on the macro scale, where you have uh, the same design fabricated out of by laser cutting, and then we have connected springs here, and then by giving an input, you can stretch the springs, and the springs can be calibrated, the stiffness of the springs, and then you can get the same stiffness back from the formula between the deformation of the mechanism and the stretching force. And this can also be used for characterizing PDMS membrane. So you can connect, instead of having springs, now you can have a PDMS membrane which kind of more closer to a cell. Um, and then that can be stretched, and then you can get the properties of PDMS again using the same formulas that connects the deformation of the mechanism and calculates the forces. Now, once we are done with those, we can also do some experiments at the micro scale. So here we are manipulating again this biaxial stretcher using an optical fiber. So this optical fiber, from the deformation of the optical fiber, you can actually know what is the force that is being used to manipulate it. So this optical fiber based transducer was developed by Professor Pramod Pulakart at RRI, and so we went to his lab, and then there we did these experiments, and again using our relations we could verify what is the force, and then we could match it. So we could verify the relationship even at the micro scale. Now once we have done those verifications, now we can actually go and stretch a cell. So here you have a single cell that is being stretched by this mechanism. So you can see that this is probably at very low stretch, and then as you stretch more, you can see the cell area is increasing. And then from the deformation of the mechanism, we can calculate the forces, we can convert that into stresses, and then we can fit some kind of anisotropic, this is actually a 2D funks model that we have fit, and from that you can calculate the anisotropy of a cell. So this we believe is the first estimation of cellular anisotropy using a mechanisms approach. This is for single cells. So this particular work was done for glioblastoma cells, which are actually neuronal cancer cells. Now moving on from biaxial stretching to something like, let's say, shearing. So now how can we do shearing? So again, we try to conceptualize it in a way that can be then turned into a mechanism. So so let's say we can have, let's say, a fixed beam and a moving beam, and then we can trap a cell in between, and then so we can actually coat some proteins on these beams so that the cell would actually go and attach to the beam. So then you let it incubate for some time, and then the cell will attach. And then now if we can actuate one of the beams, then you can actually shear the cell. Okay, so this is the overall conceptual idea on how to shear a cell, and then this is the mechanism that we have created in response to that to that conceptual idea. So where we have a fixed pose, and this is the moving beam, and the cell will have to be captured in between these, and we'll have to attach to both of these. And then the horizontal motion of the beam is ensured by this folded beam structure, much akin to the structure that Professor Gandhi was talking about in the last talk. And then we had done some calculations using FEA. Then we realized that for force calculation, we need to do a little bit more, because we are expecting forces of the range of 1 micron or 1 micronewton or less than 1 micronewton from the cells. So then we have used a DACM to enhance the displacement, and even that was not enough. So then we had to use actually we are coupling it with a bistable mechanism, which gives a negative stiffness to remove the to reduce the input stiffness of the compliant mechanism. So I'm not going into a lot of details of the calculation, just to give you an overall picture of what is the design. And this is the design in action at the macro scale. So you can see we are giving an input force here, and you can see that this is a rubber specimen that has been kept here. You can see that that actually tilts, so that is the shearing happening, and this is the bistable mechanism that has been coupled, and this is the uh, parallel beams which ensure that the motion is in the horizontal direction. So now this is where this device is right now. We are working on the microfabrication aspects of this. Again, we move to the next device for twisting. So how can we conceptualize this device? So in this case, what we are trying to do is we are trying to have a substrate. So in the shearing case, we had two substrates. You could see them from the top, and then we are moving one with the other. But in the case of twisting, it is actually more complicated, because you want to rotate something. So here what we are envisaging is we have a substrate which is below, we have the cell on top, and then we have a mechanism overhanging on top, and then we want to rotate the mechanism. So here the twisting axis will be perpendicular to the plane uh, of what you are seeing right now. Okay. So here, so we want to have a gripper which will hold the cell, and then we let the cell adhere. So here we are kind of representing how the cell will adhere to the bottom as well as to the mechanism on top, and then we want to twist this mechanism. We want to rotate the mechanism, and the mechanism should rotate about the center point, kind of similar to the remote center of motion mechanism that Professor Gandhi was talking towards the end of his talk. And what we are expecting is that, I mean, this is not a very good animation, but essentially we are seeing that the cell will be attached to the bottom, and then the top part of the cell will be twisted. So this is how we want to get the cell twisting done. So we have um, made a remote center of motion mechanism, but using flexures. So here, so one of the constraints that we have in the kind of mechanisms that we want to build is that because we are looking at cell manipulation at the micro scale, we don't want to create 3D mechanisms. We want to create only 2D mechanisms, because 2D mechanisms are easier to fabricate using lithography. Okay, so we want to be able to, whatever manipulation that we want to be able to create it using a 2D mechanism, because otherwise using lithography and mass fabrication will be very difficult. So here we have a 2D mechanism, and this is a glue stick which has been stuck to the mechanism as well as to somewhere below, and you can see how it works. So this is a design using these flexures, which works essentially based on the idea of a parallelogram mechanism in rigid body mechanics. So you can see that when you put a force here, you can see that this point is relatively stable, and then about that point, the entire this part of the don't have a pointer here. Okay, so this works on a parallelogram idea, the idea of a parallelogram rigid body mechanism, and these flexures are where the hinges would be. And then when we put an input force somewhere over here, what happens is this part of the mechanism, the bottom part of the mechanism, rotates about this point. Okay, so you can, I'll just play the video again, and then you can see how the mechanism rotates about this point, and there is hardly any motion about of this point. And right now we have been able to do somewhere up to 30 degree of rotation. So you can see that there's an input from the top, and then at the bottom that is relatively stable and it is rotating. So we are going to use this idea to actually twist a cell. Again, this we have done it at the macro scale. Till the macro scale, we have to still work on the micro scale and experiment with cells. Moving on to another topic. So here till now, what we have seen is where the mechanism is putting some force on the cells, right? But what people have also realized is that cells respond to the passive mechanical signals. For example, whether the micro environment around the cells becomes stiff or less stiff, the cell changes its properties. Okay, so we were trying to build substrates for cells, and the property of the substrate will change, and to see what is the response of the cell. So here, so this is in collaboration with Safan, who is one of the organizers of this conference. So here we have built a mechanism. So if you see here, so this mechanism uh, uh, is similar to this auxetic structure, and then we have connected a few switching elements here. So these elements, if they are engaged, then what happens is the mechanism is connected. So these points, this, let's say this north and west points, are connected by a rigid linkage. So the stiffness between those 2 points are actually infinite. So in this case, the cell will experience what is known as a positive Poisson's ratio. What it means is that if the cell pushes out, then the top part will actually contract in. So the substrate, the cell will think of it as a substrate with a positive Poisson's ratio. But now, if you actuate when you switch this mechanism, and then you can disconnect this north and west points. So then what happens is this substrate switches to a negative Poisson's ratio kind of mechanism, where when you push out, this point will also push out. So you can switch the property of the cell substrate from a positive Poisson's ratio to a negative Poisson's ratio by using these compliant mechanisms. And for that, work has been done mostly by Safan's group, where we have used a combination of multiple bistable arch curved beams to actually effect this idea of going from a zero stiffness between these points to an infinite stiffness between points. And this was presented in the IDETC in 2023. We're also working on a journal paper on that type. Now moving on to another kind of microorganism. So we are all very familiar with our cells, but probably we are not as familiar with what is known as diatoms. What are diatoms? Diatoms are actually unicellular algae which is found in marine and freshwater. So so these are the primary plants of the ocean. So they are roughly responsible for roughly generating 1/5, around 20% of all the oxygen in the atmosphere. They are found in all kinds of water, fresh water, sea water, etc. Now, what is the one of the most fascinating aspect of diatom is that the cell wall of these diatoms are made of silica. So they're literally living in glass houses. So these are some of the various kinds of diatoms that you can see around in the world. There are several thousands of species, and they have very intricate shapes. Okay. So what is known is that this climate change, and especially change in temperature, salinity of the water, is known to change the morphology of this shape. So for example, let's say you had a very pennate shape, and then the length of that thing is changing, and there are a lot of pores on this, and the pore architecture is changing. So we know that the shape of these diatoms are changing in response to the climate change. But what we don't know is how does that affect the mechanical properties, and that is important because the primary purpose of these shells are to protect this diatom. So if the shells mechanical properties are compromised, then the diatom would not be protected, and then that would decrease the population of diatoms, and then that could cause changes in the percentage of oxygen in the atmosphere. So this is very important to understand whether diatoms survive or not, and that actually pivot. I mean, that one of the important aspects is the mechanical properties of diatom. So now, how do they stand in comparison to cells? Now, cells, the modulus is roughly 1 to 10 kPa, but when you look at diatoms, it is 1 to 2 gigapascal. So they are like really orders of magnitude apart. But we think that we can still do those experiments using compliant mechanism, because we can scale the mechanism, you can increase the thickness, you can get whatever stiffness you want, whatever force resolution we want, whatever force range we want. So for that, so previous work on the mechanical characterization of diatoms are typically used classical methods like nano indentation and AFM, and some AFM has also been there, and something called as microneedle. But essentially, they have used uniaxial compression or actually compression in this case, because they are brittle. So now what we are trying to do is we are trying to use compliant mechanisms to actually create different kinds of testing. For example, we want to do a shearing test. So in this case, this is slightly different to the previous shearing case, because in the case of the cell would attach onto the mechanism if you coat proteins, but the diatoms would not attach to anything. So we need to do a little bit different stuff. So here the design problem is thought of like this: you place the diatom between two jaws, 4 jaws, let's say 2 pair of jaws, and then you have the first motion to grip the diatom, and then in the next let's say you put this force, and then that can probably break the diatom. So again, we have been able to create something like this at the macro scale. You can see the video here. So the student is placing let's say this is a chalk instead of a diatom, because we wanted to use a brittle material like glass, and then the first input is given that will actually grip the diatom, and then you give the second input at the next point, and that can actually break. And what you can see here is we have used these two indicators as displacement amplifiers, with which you can improve the force resolution what you measure, and this will be presented in the mechanism design competition. So if somebody wants to see it, they can go and see that. Okay, so I wanted to conclude my talk here. So what are we're talking about compliant mechanisms as a generic framework for manipulation of biological microspecimens. So what I hope I have convinced you is that several different manipulation modes can be assembled on a single chip using compliant mechanisms, and we are working towards both active and passive manipulation. The passive manipulation was the switching of the Poisson's ratios, and we hope to show that in the future, once we complete the experiments with diatom, that we can use compliant mechanism on not just cells but also on diatoms, which the elastic modulus is roughly 6 orders of magnitude apart. And I'll have the acknowledgements. My PhD student Himanshu and the work on cells is mostly his PhD work. And Ravi, who is currently a PhD student at IIT Kanpur, his MTech work is the mechanism for diatom. And my collaborators Safan and Pramod Pulakad at RRI, facilities at INUP ISC, where the mechanism was fabricated, the biaxial stretching mechanism, IIT Goa for all the microscopy, cell culture, and the funding agencies. Thank you.
Thank you, Professor Srinath, for an inspiring talk. Yes, we can take a few questions, and yeah, we'll pass on the mic.
Okay. So, can you just show the picture of that biaxial stretcher? Maybe I didn't understand. First, one of the first few slides. Yeah.
Yeah.
So, so you are pulling at 2 points, right? Let's say up, north, south, and east, west.
Yes.
So how do you? I mean, then somewhere along 45-degree lines, it'll compress, right?
No. So the cell is attached only to these 4 points.
Yeah. So you are pulling those 4 points.
Yes.
How do you ensure that in between, let's say along a 45-degree line, that is also being pulled? You want this whole cell to be expanded, right?
So we want the cell to be stretched in 4 directions.
Only,
Only.
not the cell to be made bigger.
No. So this is, I mean, we are trying to mimic the classic biaxial stretcher, which is used to characterize, let's say, any
Okay.
film cells that were.
So then it is not really. So in some directions, it might be compressing.
Yeah. I mean, so if the cell is attaching only to like 4 points, then it is possible that there could be compression. But what we are trying to do is we are trying to mimic the classic biaxial stretching.
So, but biaxial stretching, I would understand you're just trying to make the cell bigger in some sense, so that you need to see what stress is it? Some name is there, no? So some the expansion. You want the cell to expand, I would assume. No.
Okay, so what we are trying to do is we are stretching
Like a
in both
pressure. You don't want to create like a pressure inside, so that the whole stress.
No, I mean, it is possible. I mean, so this with these 4, if we have only 4, then it is possible that along the diagonals you can get compression.
Okay, good.
But we
I've
can
understood. Okay, here.
I know it's a generic question. So all these things might be helpful for the medical practitioners to study. So have you approached them? Have you spoken to them? What are their reactions?
Yeah. So okay. So we have had some conversations with the doctors. They are not very. What would I say? Okay, they're not very happy with mechanical based techniques, because that is still something that that they are. But that, I think, is the challenge that we face as a community to convince. Actually, there is an entire community called mechanobiology community. So they're actually pushing, and abroad they are more successful in convincing the doctors to use these kinds of techniques. But in India, we still have some work to do. But I think
All the best.
See, one of the possibilities of application for these could be like you see there are some diseases which make the cell stiff or less stiff.
Yeah.
Okay, so that can be like one kind of a
Yes.
diagnostic kind of a way of like looking
Sure.
at the things.
Yeah,
Okay,
yeah.
that could be one of the possibilities to kind of but you need to kind of, okay, if you see from the some commercial angle perspective, you need to kind of say, okay, this is in some sense better technique or some less cost technique as compared to the existing techniques. That's what
Exactly.
you
Yeah.
need to kind of work
Yeah,
on and
yeah, yeah.
see.
Yeah, sure,
Okay,
sure,
yeah.
sure. That's the idea.
We are almost cutting into the technical sessions time. So with that, we would like to end this. With that, we would like to end this invited talk session. I would like to invite Professor Lakshmana from the MA department to present a token of appreciation to our speaker. Thank you, Professor Srinath. Now we will move on to the first set of technical sessions, which will take place parallelly in the seminar halls 1 and 4, which are right across the corridor where we had tea. I request you all to proceed to the session of your choice. The list of the talks is put up right outside this auditorium as well as in front of the seminar halls. After that, we'll proceed to lunch and we'll have volunteers guide you to the location of the lunch at 1 o'clock. Thank you very much. We can leave it here. Utrecht University of Technology in the Netherlands. His research focus is on mechanism design, in particular compliant, balanced, and other odd mechanisms. He has published in various international peer-reviewed journals and conferences and has received several international awards. He is an ASME fellow, board member of several international conferences, and co-founder of Mechanical Sciences. 8 startup companies have emerged from his research, and he has held visiting positions at Laval University, Canada, and at MIT. With that, I will let Professor Herder take over the stage. Thank you.
Thank you very much. And indeed, it's a great honor, and it's humbling to be here as an invited speaker for the Professor Ashok Mida Memorial Lecture. I entitled my talk Precision Compliant Mechanisms. Let me see if I can get it on the screen. Oh, here we go. Yes. So precision compliant mechanisms to emphasize the potential, but at the same time also the challenges for compliant mechanisms. So I will be talking a bit about Professor Ashok Mida, as I have known him. Then we will move on to characteristics of compliant mechanisms. And as a consequence, that will lead to some strategies to improve their behavior. And at the end, I'll talk a little bit about trends for the future. So let me first introduce myself a little bit. So what you can see here on the top line are a couple of projects that I've been working on. So on the top left, you can see graspers. This particular one has only one actuator and 4 degrees of freedom, so it is self-adjustable, under-actuated, as we got it to know. On the right, you can see a couple of robotic mechanisms. The second one is going very fast, yet precise by internally dynamic balanced mechanisms. We also worked on parallel kinematic structures. This one is particular because the end effector is not a rigid body, but it's also a mechanism that is actuated from the base. So you can do gripping, for instance. And then my PhD topic, which is actually still going on. I still didn't find all the answers. Static balancing, where we can move structures against gravity or other conservative forces like spring forces by making a constant potential energy so that they have no preferred position. And therefore, they're as happy in any configuration that they are. So you can move them very easily. And we'll get to that also in the realm of compliant mechanisms. Now, in the bottom line, you can see a few projects that have been more recent. And I guess you immediately see the difference. I usually present this as a quiz to my students. Do you see any difference between the top and the bottom row? And then after a while, yeah, they move because they deform, right? So, and of course, we know it as compliant mechanisms. And actually, much of what I've shown in the top line, I'm now converting into compliant embodiments. So still the same principles apply, but now I am trying to configure them compliant. And today I will show you a few of them. Now, Professor Ashok Mida is oftentimes considered as the father of compliant mechanisms because he stimulated the field tremendously. Here you can see part of his CV. He has been active in multiple universities, both in engineering and technical things as well as in management. He has become known, of course, for his work in compliant mechanisms. But I would say to the people who worked with him, they will also remember him for his humanity, his passion, his way of stimulating one and all, including young people. And that's also how I know him. He was always very gentle but persistent, and that's how he pushed people to expand their limits and push their projects. Um, Also here, both in technology as well as in his management, because he established a lot of things in the improvement of buildings and everything. So this is the concept that he has become known for, pseudo-rigid body modeling. And the idea is as simple as beautiful. Namely, of course, on the left, we can see a cantilever. And okay, the end tip traverses some trajectory. And you can approximate that by an arc. And of course, that's a bit crude. But actually, it's not as crude as one might think, because on the right figure, you can see that it's not so bad after all. Even to large angles in the order of 70 degrees, it is still quite accurate. And what is even more striking is that, of course, a cantilever is not only a mechanism, it's also a spring. It has elastic behavior. And if you put a linear torsion spring in the same joint, then also the deflection behavior can be modeled quite accurately through that same range of motion. So that's amazing. And he builds on other work. I brought with me a model from our mechanism collection. Well, it is not as much as other collections, but we do have some models. I do not know exactly how old this mechanism is, but if you look carefully, it's probably hard to see from far away. You can see that the motion of this cross flexure is approximated as a rack and pinion motion, a rolling motion, pure rolling motion of a circle on a flat line. And that also worked quite nicely. If you look at it, you will find it's remarkably accurate. But of course, kinematically much more complex, and there is no spring in it. So this seemingly simple concept is very strong and versatile. And moreover, it allows people to use the knowledge in linkages to be transferred into the realm of compliant mechanisms. So also the linkages workshop that we had serves compliant mechanisms to an extent. Thank you very much. Yeah, I found a few photographs on my hard drive from the ASME IDETC conferences. This is in 2012. And I remember that sometimes he represents his students, of course, if they cannot make it to the conference. And sometimes he had a double slot, or two presentations, one after the other. And then he turned that into more of like a lecture on compliant mechanisms, where he revisited the basics and then extended and elegantly included the contributions of his students into this talk. I think on the left, you can probably see him in his element, explaining concepts to students. This is actually one of my former students. And I believe he enjoyed that very much. And so did the students. And you can see a group picture of a couple of us from the same conference. And of course, here we can see Larry Howell, one of his students, who got infected by the compliant mechanisms virus and extended his work and wrote several textbooks on the same subject. But you can also see young versions of myself, Charles Kim, Jonathan Hopkins, Dennis Brouwer from Twente University. So it's yeah, nice to dig out these pictures. I will show a couple of examples of work that directly builds on Professor Ashok Midda's work. That's what I will start with. But first, let me just give you my take on compliant mechanisms. And I often use this picture of a tree that is loaded by wind. And it survives because it yields and it folds up the leaves to reduce aerodynamic drag. And once the wind is gone, it re-erects and it opens up the leaves and it survives and it is back in the original position. That's a great strategy, but if you look at the building or the mechanisms and machines that we build, they're more like this structure here on the right. They also survive, but they are rigid. So it's another strategy, and it may work, but it's not the only one that works. So and I guess we're trying to expand the range of application of this kind of mechanisms. They are flexible and strong. Typically, we think rigid is strong, flexible is not strong, but that's not right. It's just soft. And here you can see an example of a surgical gripper, pin in hole joints, stainless steel. You know, the typical engineering solution, but it does not work because they have to be sterile. So they're sterilized in an autoclave. They are completely dry, and there's no lubrication whatsoever. And then we have stainless steel on stainless steel. It's one of the worst combinations for low friction. So we went about and changed it into a compliant mechanism, much like this. And yeah, then we got confronted by the fact that in the plane it works actually quite well. If you give it to a surgeon, they do not only grasp, they also pull and twist and everything. So the out of plane loads are very important. And it was nice to see in Professor Gandhi's presentation that there are mechanisms that survive external loads quite well. So the advantages are also already described, essentially because they are monolithic. That comes with a lot of advantages. But the kinematics and the kinetics are intertwined. You cannot separate them. It moves, and if it moves, it will generate forces. Also, if you put a force on it, it will move, right? So you cannot study them separately as we typically do in linkages. So therefore, the design is more complicated. We do not have pin joints anymore because everything moves in a strange way. And then, yeah, we get to probably the theme of this presentation. The motion stiffness is supposed to be low, but it is not zero. And the support stiffness, which is the stiffness in all the other directions, is not infinite as we have it in rigid link mechanisms. And the ratio is therefore something that we are always after to improve that ratio. So here we have a flexure, a leaf spring, and yeah, so what we see here is some arrows. Red ones are the constraints, green ones are the motion directions, and the double arrow indicates rotation. So yeah, I have one here. Flexure typically has 3 rotations. This is the main one, but it's also pretty soft in torsion, and it's also pretty soft in endpoint rotation. So yeah, 3 degrees of freedom. And this is how we traditionally study them, right? We model them, typically Bernoulli, Euler or similar, and then we make a lot of assumptions, and then we end up with linear beam theory, which works quite nicely for relatively small deflections. For the students in the room, this is what I also hand out to my students. It's an overview of all kinds of design principles, including compliant mechanisms from a company in the Netherlands, Janssen Precision Engineering. And they provide an overview of all these linear beam theory approximations for many application situations. So here on the top line, we can see the endpoint bending that we saw before, but also endpoint moment, distributed load, etc. And so it's nice to see that they provide not only the force in the motion, the stiffness in the motion direction, but also other kinds of things like stress and some constraints, stiffnesses, and all of that. Very nice and convenient. But then, of course, limited to small deflections. So that's where our PRBM comes in. And we also work a lot in our lab with PRBM. And one perhaps interesting application or extension is this study of a tubular holy sheet, if that is a word. So basically a tube with holes in it. The holes are circular on the outside, but elliptical on the inside. And if you compress it, it shows a strange behavior shown on the right. It's not exactly buckling, but very close to it. And as you can see, as you compress it, it also shrinks. So we have a negative Poisson ratio. And in order to study this behavior, we tried to catch it in a PRBM model. And by using revolute joint and spherical joints together in a structure like this, we were able to capture this necking behavior as well as the force deflection behavior, again with just linear springs in the joints. And of course the spherical had multiple springs in them and the revolute just one. But I found it amazing to see that also in these cases, this relatively elementary concept of PRBM also works. Very nice. This is recent work by one of my students, Domas, and he was bothered a little bit by the computational complexity of the kinematics, and he proposed to add another joint in a flexure mechanism. So the conventional clamped PRBM would have two joints, two revolute joints shown with kappa. He proposed to add another one, a prismatic joint with a linear stiffness K. And that basically eliminates kinematic constraints, so you can move it all over the place. But then he said, well, you know, if you are a little bit careful with the selection of your parameters, so the stiffness K is typically quite high because you are stretching a link. So if you are a little bit careful, then and you minimize for elastic potential energy, then he showed that you can get pretty good behavior. So he used this as an example. So it's two endpoints, an intermediate body that's connected by these struts. Imagine that if you compress it, it will start to rotate. And he showed here, you can see some images on the screen. Perhaps you recognize the double dots. One is the fixed point and the other one is the pseudo joint. The prismatic joint is not visible, unfortunately. But in any case, he shows that he has the initial position, then he moves it endpoint to another position, and then the intermediate body will follow in a kind of compliant fashion. But if you then minimize for potential energy, you will find a realistic endpoint position. So he also tested it. Here you can see the same thing under a compression test. And the solid line gives the simulation. The dashed line gives the measurement, where we have to take into account its viscoelastic material, basically. So we might expect a little bit of this kind of behavior. And also in more complex motions, compression and shear and back also seems to work quite nicely. So it's interesting because computationally it's very cheap and still it seems to work. So that's ongoing. Now, if we think about these flexures, then we have these degrees of freedom and these degrees of constraint. And as I mentioned, we always want to maximize the ratios of stiffness in the constraint direction over the motion direction. Yeah, if we put flexures together, we have one opportunity to create vastly better behavior. So instead of one flexor using two, for instance, in a cross arrangement for a rotational joint or parallel for a linear joint, gives a much better behavior. So here you can see the linear one. But then the problem in many of these is that the behavior is quite well in the original configuration. However, when we deflect, then we lose a lot of support stiffness. So here you can see a diagram of several rotational compliant joints. And this is the second natural frequency, which represents the first undesired mode, so to speak, typically one of the off-axis stiffnesses. And you can see that in the neutral position, they are all pretty good, but as soon as you deflect a few degrees, then the support stiffness drops dramatically. And that is a challenge. And several of the projects that I will show are about improving the ratio of support stiffness versus motion stiffness. Yeah, so that is summarized here. So some of the techniques that we develop are, their purpose is to reduce the motion stiffness, the intended degree of freedom. Other efforts are aimed at increasing the support stiffness, the stiffness in the undesired directions. So let's have a look at a few of these. One of the things that we have been working on is so-called torsion reinforcements. If you consider the flexure and we deflect it, it is fairly stiff laterally in the original configuration, but it's soft when it is deflected. And what we see is that the proximal part of the flexure twists. So if we can constrain the torsion of that region, then we would have better behavior. And one idea was to put a bellow in parallel of the flexure. You might think of the flexure inside of the bellow so that they are working as a unit and then they can still bend. The bellow provides 5 degrees of freedom, but it's very stiff in torsion, like your vacuum hose cleaner hose. So if you put them together, you get something like this with a little bit of imagination. And maybe after the talk, you can try this design where you can remove the connection between the elements that are perpendicular to the flexure itself. Then it will be very soft in torsion. But if you put it back together with the pins, you will be able to perceive the change in stiffness. So that was done here. And for instance, if you take a so-called folded flexure like this, it's a leaf spring on top of another leaf spring, and you apply these torsion reinforcements, these triangles, then you get something like this. It can move in the plane. Actually, it has still 3 degrees of freedom, x, y, and theta. And it is important to observe that the compliance is still distributed. Initially, one might think that it is now concentrated in these junctions, but it is not. Actually, on the contrary, the junctions have become fairly stiff. But as it deflects, the triangles deflect along. So everything deforms very nicely and is still distributed, no stress peaks. So we get a planar mechanism, basically, a planar joint. The end effector can move in the plane, as is shown here. One thing we did is take 2 of these elements and connect them together. So both of them can do a plane, but if you connect them together, they can only do what each of them allow. So that is the intersection of these planes or the line. So what you then get is that the mechanism can only move on the intersection of these planes, as shown in this video. I also brought a demo of this one, but the frame is pretty compliant, so it is not optimal, I would say. But nonetheless, you can observe that it can move relatively easy, and the torsions and the other directions are constrained. Now, in the previous example, the triangles are prismatic, but you can also imagine that you make them conical if you can do that with a triangle. But in any case, that the panels intersect at a point, and if all of those panels intersect at one point, then this becomes a remote center of motion, remote center of rotation. So it was at infinity with the prismatics, with the prismatic triangles, but now we get it closer and it becomes a spherical joint. So it now has 3 degrees of rotation in both directions, but also the actual direction of the stylus is a degree of freedom. And this video shows how it works. I was unable to embed it. So let's see if I can bring it up here. This one. So this shows that you can move it around, but that the point of the stylus is a stationary point. This is the actual rotation, which is still rather stiff. Currently, I have a student who is trying to make it such that all of the stiffnesses are equal, isotropic. And here you can see a variant where we still have the triangles in series, but nested into each other. So it becomes much more compact. But of course, the behavior is the same. So we created a spherical compliant joint in this way. And I also brought a model with me where colleagues from Italy used this joint to create a fully compliant monolithic delta robot. It's also outside. Okay, and a recent design is this one. It's a compliant Soros mechanism in a way, where we have a base and an end effector. And from the base to the end effector, we have these main flexures. And they are torsion reinforced by the triangles that are on top and below. We actually optimized the number of triangles, and we found that one is already enough to get a very significant improvement. And adding more than one does not really help that much. So also for manufacturing purposes, we opted for just one. Again, here you can see the FEM analysis that shows a very nice continuous behavior, distributed compliance. And the main purpose of this particular design was to make a linear motion that was very precise for some applications in the semiconductor industry. And here you can see some of the performance. The total stroke is 5 millimeters, but the top end was the most critical one. And in that part, 140 micrometers, the deviation from the perfect straight line was only 5 nanometers. Yeah, okay. Another strategy is the following. Many or most, by far most, I would say, compliant mechanisms are built such that the flexures are initially straight and unstressed, even advanced ones like on this slide. And as we saw before, that makes sense because then in that position, the performance is the best. But also, you know already that once it will deform, performance will drop. So what if we start out with curved flexures? Then we do not start in the best possible configuration, but as the mechanism deflects, some flexures will get even more curved, otherwise will straighten. So they kind of take over the loads on the structure. So here you can see a straight line mechanism, and it was optimized for straight line motion. So over this stroke of approximately 20 millimeters, I believe, the deviation is less than a micrometer. And at the same time, it is also optimized for support stiffness. In this particular case, support stiffness perpendicular to the trajectory, but in the plane of the mechanism. So that means that the support stiffness has become constant. Not great to begin with, but constant over the whole range. So that if you would put a load on it, it would still traverse a straight line motion. And finally, it was also optimized for the second modal frequency because we were afraid that these intermediate bodies might be affected by vibrations. But it is in a couple of hundreds of hertz, even without removing some material. Other work with initially curved flexures includes this one. it actually comes from a problem in rehabilitation engineering, and some people need some support if they want to move because their muscles are affected. And the thing is that if you sit upright, then you're basically an inverted pendulum. So if you lean forward too much, you will not be able to get yourself upright again. So the idea was to provide a support that would provide some counteracting force. And for convenience, this mechanism should be asymmetric so that you can easily take it away. But the stiffness ideally should be symmetric because then you can lean in both directions. So we selected a beam with a certain cross section, something like this, and we optimized the shape for the stiffness behavior. And here you can see what you get in terms of the colors. The ISO lines are the forces. What you get if you just have it like this. But if you optimize it for certain parameters, then you can create a much more symmetric stiffness behavior out of an asymmetric beam. Quite interesting. Later, we also made it adjustable by shifting a bellow over this profile. So you would have a disc, actually two discs, with holes of this shape in them and a bellow in between. So you can shift the whole thing up and down. And you can imagine that if you shift it, this is shown here. If you shift it down, it will be quite stiff because it constrains the torsion in the proximal region. Whereas if you move it up, then this region is not affected and the whole thing is a lot softer. Finally, we optimize it such that in one direction there would be no change of stiffness, but in the other direction there will be a large change of stiffness and still symmetrical. Another method that we are developing is the following, where we design not only for geometry but also for stress at the same time. So on the left here you can see a cross flexure, and the colors indicate the stress that is developed in the flexures. And what we can see is that, of course, there is significant stress towards the extremes. But it's also important to note that the maximum stress is asymmetric. So, for instance, if we look at the bottom left point, then if we go to the left, like now, it's completely red. But if we go to the right, it is just bluish or greenish, right? So let's consider the compressive stress at the surface on the left side is much higher than the compressive stress on the right side of the flexure. And this asymmetry can be employed by putting some tensile energy, with some tensile stress in locations where the compressive stress will be large, and conversely, we put some tensile stress already in locations where the compressive stress will be large. So say that we have like 100 on this side and 20 on that side, then we can balance it out by putting in already 40, so that in the end we get 60 on either side. How do we do it? It is already shown a little bit in this right video. Yeah, so I will use the next slide to explain it actually. What we do is that we take a first step. We design the mechanism as we should do normally, okay? Then we consider the stress in a mechanism, and we design a desired initial stress state. So as I mentioned, we put some compressive stress where a lot of tensile stress will develop and vice versa. From that, we create kind of an imaginary load on one of the points. We call it a release point, could be any point, in this case the bottom right point. So we design a load here that generates this desired initial stress state. And then we do an inverse FEM analysis to find the location of the structure that would get to the desired position with that load. Okay. So normally in FEM you have an unstressed situation. You put a load on and you calculate the deflected state. Here it's different. We have a state that we know with a load on it, and what we want to do is take out the load and see where it ends up. So in this figure here, if we take out the load, it jumps back to this position. And we calculate that using FEM. So it's very similar. The mathematics are basically identical. The only thing is you change the initial state with the final state. And you know that there's very likely a solution. So that's an added benefit. So then what you do is we manufacture it in this calculated state. We then preload it so that we apply the load basically and introduce the stress into the mechanism. And then we have the initial configuration that is geometrically exactly the same as the original one, but now includes the initial stress that we like. The difficult step, of course, is to design our desired stress situation. And this illustrates a little bit how it works. For instance, if we have a load on a cantilever, then we can calculate the moments, and they depend basically on the endpoint load that we provide, and that gives us an idea of how we can create the desired situation. For the cross-flexural pivot, for instance, already as I mentioned, we want to create some additional compressive load on the outside here. And we can do it by applying a pure moment, if I remember well, on this point. So that's pretty much how it works. We have this calculated manufacturing position. We preload the mechanism, and then if you deflect it, then we can see that in the ultimate state, the stresses have become less and that it is also more evenly distributed. So here in this graph of stress versus actuation force, we see the traditional cross flexure. And by introducing the preload as described, we can create a situation that has lower stress and lower preload, or even lower stress and the same actuation load, I should say, or anything of this nature. So these blue dots are all feasible solutions. The three red ones were the ones that we actually built and tested. The same method, but then in a folded flexure, is shown here. Again, we calculated the manufacturing position that gives us the desired initial stress distribution. And then if we actuate it, we can do one of two things. We can design it such that we reduce the peak stress over the range of motion, or we can design it such that the actuation force over the range of motion gets reduced. And that's the one that I brought with me. It's also outside on the table. On the left, you can see the conventional one. And of course, it's a spring, it moves back. On the right, you can see the preloaded one. So initially, it has the exact same geometry, but it has initial stress in it already. And therefore, it also carries elastic energy. And that energy is basically used to deform, to deflect the flexures. And therefore, if you do that well, the potential energy is constant, so you don't have to put any effort into it in order to relocate it. Okay. So that's the idea of, so we end up basically with a statically balanced compliant mechanism out of a single element. But that's a nice bridge to another strategy that we're working on, which is static balancing. Static balancing in principle is well known. Especially in the Netherlands, we are confronted with static balancing pretty much every day if we cross a bridge. In the old days, the captain of the ship would be typically by himself. So he would get off the ship lift the bridge with one hand, just based on the counterweight, and then he could pass on. But also, this is a famous example of a desk light. This particular one, Angle Boys, is mathematically perfectly balanced, by the way. The most of the ones that you buy in a big shop with yellow and blue is not particularly well balanced, but you can do it because also here the mass and the spring can exchange energy, right? So essentially any conservative force can be used for static balancing. And on the right, you can see a project that I worked on a while ago, where the cosmetic covering of a hand prosthesis is considered as a spring, which affects the behavior. It takes effort to extend that covering, represented by one spring, which can potentially be balanced out by the other spring, which makes not only motion much easier, but also the forces that are operated have a much better relationship with the activity that people are doing. Okay, and for convenience, we typically use potential energy equations to calculate these things. So if you look at the energy, then in a regular compliant mechanism, the energy that we put in is partly used to deflect the mechanism, and therefore only partly comes out. So in terms of a transmission, it implies that compliant mechanisms are always poor transmissions because you never get out what you put in. And that is a bit disturbing until we realize that this energy is not lost, it is stored. So it's not dissipated. So if we have an energy storage that provides energy at the same time when it requires energy for deformation, then we can make a statically balanced system where one part of the mechanism requires force for deformation, and at the same time, the other part of the mechanism provides some energy. So it does require that it is preloaded once. You have to have some energy on board, otherwise you will not be able to balance that mechanism. So there should be some means of preloading. And so yeah, in the macro world, it's pretty easy. You can pull a screw or put something else. In micro mechanisms, that is more challenging. Here you can see another example. Again, a cross flexure. On the top left, you can see the cross flexure by itself. It's pretty stiff. You can see it by the oscillations. And on the right, by the way, designed by PRBM methods, you can see leaf springs that are initially flat are then preloaded and assembled. So they contain already some energy. And they give the energy to the cross flexure as it moves. So here on the right, you can see that the behavior has completely changed. It no longer oscillates because the natural frequency is zero because of zero stiffness. And it can be moved very easily throughout its range of motion. We often use also preloaded post-buckling springs, if you will. Here you can see an example together with Charles Kim, who was one on the group picture before. And you can see that a gripper with a positive stiffness here on the right is equilibrated by these preloaded leaf springs in post-buckling regime. And yeah, for quite a range, you can make a fairly nice balanced system. This is one of the classical designs from, I believe, still from the Philips times by Jan van Eyck. Same idea. We have positive stiffness from the leaf springs of a parallel leaf spring guidance, actually a double one. And we have negative stiffness from this buckled flexure. And what happens if you turn this knob is that the central part is twisted. So that's another way of tuning the stiffness of this post-buckled behavior. And you can see from the natural frequency that you can get it quite right. And this is perhaps also an interesting example of a 4-bar linkage with compliant joints. And together, of course, they provide a positive stiffness to this mechanism. And here you can see again a couple of preloaded flexures that statically balance the 4-bar linkage as it moves. And on the right, you can see the testing that was done. It's always difficult to experimentally assess the behavior because we basically measure a zero force, which sometimes becomes a little bit positive, sometimes a bit negative. So what we often do is put a dummy load. It's hard to see, but there's one cable going to a dummy load and the other goes to the tensile tester. And then we subtract the dummy loads to get the full behavior. Finally, static balancing is also nice for vibration isolation. So what you can see here is a combination of positive stiffness, this one, the blue line, and negative stiffness, again, buckled beams, the green line. And if you put them together, then you add them up and you can tune it such that you get a region of zero stiffness. So this is where it's statically balanced. So you have to enter it into that range and then it will have very low stiffness. And here you can see that actually in 3D, 6 degrees of freedom. So here you have the buckled beams. This is the positive stiffness. And if you put a load on it, this one, it enters into the zero stiffness regime. And then you can shake it. And yeah, the vibrations are perfectly isolated because we have zero stiffness. Interesting. So I've been involved quite a bit in static balancing, and there are many advantages. Of course, there is less energy consumption, as we saw from the bridge already, but also in compliant mechanisms. Very important also in precision engineering is that if there is less resistance in terms of stiffness, then also the actuation forces can be reduced. And actuation forces are generated by an actuator, which generates heat. And heat affects precision quite a bit in modern machinery. Also, there's increased safety because if there's a power failure, the system will simply stay as it was. In the surgical gripper, we saw that also removing undesired forces from an information transmission improves the signal-to-noise ratio. And we can also eliminate backlash, for instance, by preloading vibration isolation I mentioned. So yeah, many things that we can do with static balancing. And for compliant mechanisms, especially relevant because much of what we do as mechanical engineers is making transmissions after all. So therefore, if we can use static balancing to improve the efficiency, then that is potentially very impactful. A couple of specials are here, which can be switched. I have one that can be perhaps seen from the audience, where in the original configuration, the mechanism is very stiff, but it can be preloaded. And from then on, we have energy on board, which can be redistributed over the flexures. And then all of a sudden, the movement becomes much softer. What we in fact do is shown here on the right in the diagram. We have two characteristics that we shift together, and then they add up into a flat region. And then we eliminate the stiffness from the equation. So it's nice to feel after the lecture. So again, if you compress it this way, you can move it with very low stiffness. More recent work is shown here. Again, a video outside. So again, quite stiff. Doesn't want, it has extreme high resonance. Then if we toggle it, the flexures that initially triangulated our platform have now become beams in post-buckling, and they statically balance the guiding flexures that are shown here and there. It's reversible, so we can switch it back. So imagine that you have a delicate instrument that you need to transport or to launch into space. So once in orbit, you switch it back, and then it has become your sensitive instrument again. And the ratio between the soft and the stiff mode is in approximately 1,000. So that's one of the things that we also try to improve. A spatial arrangement also done with PRBM. This is a homokinetic coupling, so a pure transmission of angular velocity, so constant angular velocity into a constant angular velocity in spite of this range, by essentially a parallel kinematic structure that is symmetric in the midplane, and then we can achieve this kind of behavior. We also work on spatially curved flexures. And one of the reasons essentially is that flat flexures, they buckle quite dramatically. But if we create spatial shapes, then we can extend this buckling process over a longer range. And that allows us to create all kinds of force displacement diagrams. From constant force to increasing or decreasing, or sines and cosines and those kind of things. And here you can see some work on the reverse of this, where if we have a shape like shown here on the right, then of course it has some sort of behavior. But here you can actually tweak the force displacement diagram, as will be shown in a minute. Yeah, so that is happening here. So let's push it up a little bit, and then the software calculates the structure that actually does that kind of behavior. And because that's always, of course, ideally we analysis is nice, but synthesis is even nicer, I guess. So that's one of the efforts that we're doing. I just put this slide in because we had a discussion during one of the breaks about the incompatibility of linear and angular stiffness. Yeah, they have a different unit, and they're hard to compare. So what people do is resort to frequencies. We saw an example. So the degree of freedom should have a low frequency, and all the other ones should have high frequency, regardless whether it's a translation or a rotation. So that seems to be nice, but of course, you can manipulate these values by changing the mass and inertia of the platform. So there's a degree of arbitrariness in there. Same is true if you magically pick out some kind of they call it representative length or something. I forgot the term. But in any case, so like one diameter or something of that nature. And then characteristic length, yeah, thank you very much. And then you can convert angular stiffness to linear stiffness and vice versa. So we were also confronted with this problem in our spatially curved flexure work. For instance, if you have a structure like this and you start pulling on it, then yeah, what is the degree of freedom? Is it a rotation or a translation? And we ended up considering virtual work, and that gave us a factor that relates the linear and the angular stiffness. And what you can see then is that in this particular case, this is the compliance on the vertical axis. So the highest compliance first is a rotation, so the endpoint will rotate first, but as you pull it out more, at some point it starts to translate, so that's the red line here. So here you can see the crossover. So at larger deflection, you basically kind of translate the endpoint rather than rotate it. So that was one way of how we try to deal with this this problem, because yeah, there is always this difficulty. And we are trying to explore this field of spatially curved flexures. We think it's quite promising, but there's of course an infinite number of shapes that you can imagine. So we're trying to create a sort of library of certain basic shapes like spirals and those kind of things. Here you can see a few examples, corrugations, of course, so that we have these diagrams available and can put them together in our designs. And oh, sorry, I was going to say that we composed structures for body support that go around the body. My dream is basically that we have exoskeletons that are not exorobots, but are basically shells that are close to the human body. They can move along with the physiological movement that we can do, but at the same time generate forces against gravity, so they also help us lift our limbs. Yeah, so I think I put this one in as the final slide, if I remember well, because it has, again, a number of these cross flexures. They are inherently over-constrained. The mechanism itself is also over-constrained. So there are additional flexures built in to release some of the over-constraints and create 2-degree freedom motion. Maybe one advertisement, if you will. We are trying to put a lot of cases that are common in precision industry in the Netherlands into so-called design principles for precision mechanisms cases. And we are putting them on a website from the Dutch Society for Precision Engineering. It's almost like SP, but then for Netherlands. We have about 50 of these cases right now. And at the same time, we are writing chapters, if you will, on specific topics like flexures, but also hysteresis and damping and all those things. We do it together with the University of Twente, University of Eindhoven, and the Dutch Society of Precision Engineering. And hopefully it's going to be not necessarily a book, but a source of references with industry cases along with kind of living chapters that will be adapted all the time, I guess, and handed out to our students. So it's an initiative for all of the Netherlands, but it will be open access, so basically for everybody to get some idea of what we do in precision engineering in the Netherlands. So with that, I would like to conclude and thank you very much for your kind attention.
We may have time for one or two questions, quick ones. Yeah, very good.
First of all, thank you very much for a very interesting talk. My question goes back to something that you showed in the very beginning, your statically balanced box. Okay, so you showed a video of
Oh, yeah.
statically balanced box.
Right. Yes.
The lady comes and puts something inside and it goes back.
Yes.
Now, I understand that you can make this gravity independent by balancing the
Yeah.
potential energies and so on.
Yeah.
But now what is happening is that you're changing the mass.
Yes.
So how does it tune the potential energy after that change?
Yeah,
That's the
that's
question.
a very sharp observation. So what we have here is this cabinet that goes up and down, and it is statically balanced using springs. So there are springs built inside. That's one.
Yeah.
Now the thing is, indeed, if you put something in or take something out, then the mass changes. So what we added to this system is that the spring can be adjusted.
Yeah.
Now typically the spring is heavily loaded. There's a strong force that holds the spring. Therefore, we added another balancing mechanism to the system that balances the adjustment of the spring. And this adjustment is connected to the door. So if you open the door, the balancer is adjusted all the way to the lowest level.
Yes.
So it sits very stably in the lowest point of the range of motion. Then you can take in and out whatever you want. As soon as you close the door, the adjustment goes up. It goes very smoothly because it is balanced. So you don't notice it in the door. Nevertheless, you will change the balancing until a certain equilibrium is reached, and then a mechanical brake comes in. And then it is slightly overbalanced because the brake is a little bit too late, which is nice because then the cabinet moves up.
Okay.
Yeah.
Thank you very much. Is it published somewhere or patented somewhere? I mean,
It
can
is
you?
patented, and a startup company made a product out of it, so you can actually buy it.
Okay.
Yeah.
Thank you.
It's used a lot for um, interactive screens in schools, because typically the teacher is taller than the students, so then they move it up and down.
Yeah, one question here. So it's a very nice concept, and I was curious if you have used any converging or diverging kind of curve beam in your applications. Right now, the width of these beams remains uniform.
Actually, usually we do, but the example of the straight line mechanism with the curved flexures, you will see that the flexures are not only curved, but also the thickness, the
Yes.
plane thickness is not constant.
Yeah.
Yeah, so you can optimize for that as well.
Okay.
Yeah.
So do you see any kind of advantage? Let's say if we
Well, the main advantage is that you can distribute the peak stress a bit, but you will also stiffen up the flexure. So it's pretty challenging to actually reduce the stress.
Okay, thank
Yeah.
you.
Yeah. Thank you very much just for your very nice and motivating presentation and talk. Wonderful. I have one question. When I saw all the structures, um, especially the straight line motion with the curved beams or the locked mechanism, do you have some strategies about type synthesis there, or is it just my experience, my knowledge,
Yeah.
good engineering feeling, or is it possible to?
Yeah, great question. Very often it is indeed intuition and experience, perhaps, but we also work with other strategies. We did some machine learning topology synthesis with mixed success. We end up with structures with a lot of bars that do nothing. So there's a few that take over the function. And we were not able yet to discard the ones that are useless. But interesting work, by the way. Also, we worked on topology optimization. And in fact, we had a project with a PhD student in topology optimization and one in kinematics. And topology optimization tends to generate these organic shapes. My kinematics student tried to interpret them and simplify them to get to the working principle and feed that back so that the optimizer had a better initial guess. So that way we kind of stepped back and forth forward. But the magic automatic design is still far away, I guess. Yeah.
Thank you.
I think in topology optimization, much of the creativity goes in setting the boundaries. So please.
Yeah, thank you very much. Very nice presentation. I was just curious, you showed an example of this vibration isolation.
Right.
Is it only along one direction? Is it possible to extend it to, let's say, Z and rotation about Z or any
Yeah.
other combination?
As a matter of fact, this structure is a 6 degree of freedom balanced system. So all of the 6 degrees of freedom are balanced. And the Z translation needs to be preloaded. So that preloads the Z direction, but at the same time also preloads the other ones. For instance, there are 3 vertical wire flexures. And by putting the load on, they get very close to their buckling load and then become very soft. But the shaker, indeed, in the video only shows the vertical motion, but actually all 6 degrees of freedom were statically balanced. This stage was intended for semiconductor industry where it operates in vacuum. So we would need 6 actuators to move it. They all generate heat, and the heat cannot escape. So it was very important to keep the heat as low as possible, and therefore the stiffness as low as possible. Yeah.
Thank you.
Thank you for the wonderful Q&A. Thank you, Professor Herter, for the excellent talk. I would like to invite Professor G. K. Anand Suresh to present the memento from AMM and a small token of appreciation from the organizing committee. to Professor Herder. We'll also play a brief video to show what the mechanism does.
It's cold. Oh, it's cold. Yeah. Thank you very much. Ah, thank you so much. I can see what it does. Yes.
Yes, there is mechanism underneath that operates.
Oh,
It is aluminum, but under this polymer one is there to show people. This will yield very quickly. So there is a plastic one.
mhm.
In memory of the father of compliant mechanisms, Professor Ashok Mehta, we present this memento for the Ashok Mehta Memorial Lecture. The memento features the first compliant mechanism in modern times developed by Professor Mehta. The design incorporates his initials, the crimping mechanism in the form of an inverted A, and the frame represents the letter M. A functional crimper is placed beneath the memento, wherein a force applied on the handles is amplified at the output, achieving a significant mechanical advantage. This design was conceived when Professor Mather was working with AMP Incorporated, a company in Pennsylvania, USA, to obtain high mechanical advantage with a hingeless, fully compliant mechanism. The legacy of Professor Ashok Mehta continues to inspire and live on.
A small token of appreciation from the organizing committee being presented by Dr. Anand Suresh to Dr. Herder. Thank you, everyone. We will take a brief 10-minute tea break. Tea is ready. And we will meet again here for the invited talk at 3:50. We are running about 15 minutes delayed, but we should be able to cover it up. We'll also have running tea during the technical sessions, which will be followed by the invited talk. So yeah, let's meet here in another 10 minutes. Thank you.
Oh,
You will go through this. You will
yeah.
use your own mouse.
Welcome back, everyone. So this is our second invited speaker of the day. Designing mobility systems that can seamlessly adapt to occupants with diverse needs while still enhancing efficiency, comfort, and safety is an increasingly important challenge. In this talk, our invited speaker, Dr. Umesh Gandhi, will from Toyota's Research Institute in North America, will showcase some of their work into reconfigurable and programmable structures. Dr. Gandhi is an executive assistant at Trina, which is Toyota's core research division in the US. He has a PhD in mechanical engineering from the University of Michigan and has worked for over 35 years in the automotive industry. Dr. Gandhi is working on developing programmable structures to improve vehicles as well as robots, and he'll be presenting some of his group's work today. He has over 120 issued patents, and he's also an elected fellow by two organizations, Society of Plastics Engineers and American Society of Mechanical Engineers. Without further ado, I hand over the stage to Dr. Gandhi.
Hey, thank you for introduction. And I also want to thank you for opportunity to come and present today. What a wonderful work our group is doing. So I'll wait few minutes for people to come in before I start. It seems like people are just trickling in. Okay. This was working. Yeah. Okay. On. Okay. Can you hear me? Works, right? Oh, okay. All right. I think you can hear me now. Seems like it's all connected. So I'll get started. So basically, I'm just going to go talk about uh, development of programmable physical systems at Toyota Research Institute North America. That's the group. That's our group. And just to make a point that we call it physical system because we used to call it programmable systems, and people used to confuse it with the computer systems. So these are the physical systems. So one more clarification of the presentation, because this presentation is based on my opinion and not the Toyota view on a future direction, because many times we present and some we don't want to some misinterpretation. So please keep that in mind. What I'm going to do is go over the introduction of who we are and then give you background and motivation of what we do, and then our development approach, and then I'll share some examples and also share key challenges. So Toyota Research Institute, we are located in Michigan, and main purpose of this institute is research, develop technology that can be used by Toyota in the future. So this is our facility in Michigan from outside, and this is an inside view. So this was started in 2008, and so it's over 15 years we have been working on this research. Now Toyota is a global company, so I just want to give a little idea of where we stand within the Toyota. So Toyota is most of its headquartered in Japan, and a lot of activity happens in Japan. So Japan, there are three areas. One is a fundamental research at Toyota Central Research Lab. There is advanced development that happens at Higashi Fuji Research Center. And then there is a product development. That's where the basically Toyota vehicles are developed and then goes into production. Now, Trina, that is Toyota Research Institute, we are in US and we are part of Toyota Motor North America. So that is the research and development part of Toyota in US. We are the R part, that's the research. Similarly, there is a Toyota Motor Europe. Also, there is a Toyota Motor in Thailand. And also there are two. One is a TRI, So people often confuse us with them, but that's just both Toyotas, just two different organizations, and then woven by Toyota. So what do we do at Trina or Toyota Research Institute? So we have 4 areas. So one is a material research. They basically look in the batteries and then fuel cell, etc. Then the second, electronic research. They're looking into power inverters, thermal management of the batteries, wireless charging, etc. And then the future research, that's our group, that's what I represent. We look into lightweighting, programmable materials, future mobility concept, also look into cyber physical systems, etc. And this is the specific area I'm going to talk today. And I would also like to emphasize that most of research activity, we are looking into how quantum technology that is rapidly developing, computing as well as sensing, and Gen AI can help us. So those are some of the research topics we are working on. The programmable physical system group, these are the group members, and I just wanted to show this because whatever I'm going to present is a contribution from the whole group. So this is the members whose work I will be presenting today. Also, we have many collaborators across the world. IISc is one of the collaborator, and we are very happily working with them for past many years. So motivation and background. So basically, what is the research flow? This is a typical overview in the vehicle systems. So basically, we have fundamental research that goes into advanced research, advanced development, and then we go into product development. Now, this process basically typically takes about 20 years. So our role is we look for fundamental research and we would like to see if it can be applied and develop it further into advanced development. And then it can go in the product, it sometimes may not go in the product. But our role is basically connecting that bridge. Now, when we look for something that is going to be used 20 years in the future or maybe even longer, we want to know what is needed. So that is part of the future research activity, and that is where we are looking in the future trends. What is going to change? And I'm going to change just few trends that we think are important. There are other trends that may be important. So one is the aging population. It may not be as much as critical in India, but if you look at US or China or Japan or Europe, there are a lot of people living longer, and there are a lot more people living longer. So the aging population is increasing. And what is possible is that there are a lot of people, they need more support and help, but the younger people may not be as many, and that may be the challenge that we need to find a solution to so everybody can be happy and enjoy. So that's one of the motivation for us. The other is we recognize that climate is changing, and I don't think I have to give many examples. You see it in the news every day. And there are models that are predicting how the temperature is going to change based on the CO2, increasing the CO2 in the atmosphere. So again, I'm not trying to say a whole lot on this, but those are the challenges. And what that challenges means is that we need to prepare. How do we address those challenges? And there's a lot of emphasis on reducing the CO2 emissions. So the target is about 2.5 tons. Now, if you look at all the different countries list, and this is based on the study from MIT, that the CO2 emissions are much, much higher. And all the things that is needed to reduce it is all listed here, which basically change the lifestyle. So we think that's not going to happen. And therefore, the solution is one of the solution is as the temperature changes, the world will change. Some parts will be affected positively, the green parts. The red parts are affected negatively. And then the question will be, how do we bring, what technology may help? And if we can slow it down, that may be great. But most likely we need to prepare for the changing climate, and that's a challenge for next 30 years and onwards. So some of the ideas are here have more resilient cities and multi-mode vehicles, etc. So given that future, what's the vision and what is Toyota's future mobility ideas? So there are three areas. One is we look into personal mobility, many options. The other is shared mobility, and then develop city, which is basically Toyota woven city concept, city to enhance mobility. So basically, how do we build the city and the living conditions that will make good use of mobility? So vehicles should be basically comfortable, part of the circular economy, and maybe carbon neutral, and also adapt to surroundings and the environment. So that's the goal and targets we have. Now, just to give a very quick idea on what is programmable physical systems. So our image is these are the systems that can change its physical property based upon user input. And the physical properties can be shape and stiffness, and here are some example of shape change, and this is based on EAP or pneumatic actuator or SMA actuators. And other is to change stiffness, and here is an example. Basically what you see is a jamming structure which is based on the vacuum condition can become stiffer, or it can be softer. And similarly, there are other ideas such as electrostatic clutch, which can be on and off based on the voltage, or variable stiffness material like STF, shear thickening material, which can change the stiffness based on the speed at which they are loaded. So this kind of material can help us achieve the programmable performance. Then there are other physical quantities such as electrical, thermal, etc., acoustic, and we are not looking, but it will be something we look in the future. Now, the motivation side, one is we want to improve the safety, and this is very important because there are more and more autonomous cars, and people tend to not be in the seat belt or perfect sitting position if it's all autonomous vehicle. And that's where we would like to bring in some kind of adaptability and improve the safety. The second is comfort. So seat interior can adjust to the size of the occupant or position of the occupant. And the third is just improve performance by making it more aerodynamics or make it interior more reconfigurable, so different purposes can be addressed. The second motivation is for the aging population. People are aging, they need more and more physical support, ambulatory as well as cognitive. So the idea is we would like to have robots and exoskeletons that can help. But if robots and exoskeletons are there to work with the people, we would like them to be softer. So the idea is to come up with a software actuator and sensors that can be easily integrated to work with the humans. And third is a very unique, this is a very unique concept that Toyota is working on. We call it mothership. And the idea is that we design a very high altitude platform that can harness energy from the wind. And there is a westerly wind, which is very, very high speed, but very high altitude also. So this is that's a concept. And if we can harness the energy, and we can also use this type of structure for communication, weather monitoring, etc., that maybe help the environment in the future and also the changing conditions. So this is again visionary futuristic project, and we think that programmable morphing material can help as wind conditions in this situation change a lot. So those are basically our motivation, vision, what we are doing, why we are doing type of thought process. Next, I'm going to talk about development process, and a lot of these, probably some of these points you probably heard earlier, but for our side, we are looking into more comprehensive because we need to make something that can be used in the future. So what we are saying is, if you want something that is programmable, that can be change shape and change properties. So first thing is we are looking into actuators.
So we have SMA, twisted coil, polymer, EAP. So many different actuators are possible. And each one has its own strength and weakness. Some can be more compact, some can be more efficient, some can be faster. So there are all possibilities. But we also realized we need sensors to see how actuators are working. And important, we need mechanisms. So we heard a lot about flexible mechanisms that are very important because we need to use these mechanisms to change shape, but also maintain the stiffness. And that's actually really a challenge, and I was happy to see a lot of great ideas. Also, we need a stretchable skin because whenever we work, we have realized that the skin is a very stiff material that needs like a wings, etc. And we need we need to create that which can change. And finally, algorithm and controllers. And from development side, we have design tools. We use a lot of CAE and computational methods. And we also use the prototype tool like 3D printing. So this is a multidisciplinary research, and we have many people with different expertise are together in our group, and we also work with collaborators. Now I'm going to share some examples. So first okay, this is like a big overview of all the type of different projects or ideas or areas we are working on. So one is actuators. There are many different actuators, and we are following most of them. SMA is the most closer to the application side because shape memory material has been worked for a long time. The other second topic is morphing surfaces. I heard some auxetic material. So these auxetic material are very special. If you pull them in one direction, the other side expands. So it's like negative Poisson's ratio. And when we have these auxetic material, they are used for, like I would say, grippers and many other, where they can conform to the complex surfaces and create the very uniform pressure. Other is an inflatable structure. They change shape very fast. If you think of the fastest way to change shape is the inflatable, because once you pump air, it changes. But it's hard to maintain its stiffness and energy absorbing properties. So the idea is to put it in tethers as well as use multi cells. So the inflatable structure, we are looking into how to create the cell structures. Also different type of tether systems. And once we put it, usually the airbag performance or such a structure performs much better. The material is a shear thickening material. This material has very interesting property, that is, depending on the speed at which you load, its stiffness, the shear depending on the strain rate, the shear resistance goes higher and it becomes rigid. They are used for bulletproof vest actually. So the idea is to use them for bumpers. So bumpers can be soft if somebody if it hits a pedestrian, but bumper can be stiffer if it is involved in the impact and absorb more energy. Other area is the jamming structures. Again, we want structure or material to be soft, but also become rigid when it needed. And I'll show some example. And noise and vibration, that's one of the challenge. How do we address? Using one idea is non-linear or quasi-zero stiffness springs. Also looking into different metamaterial that can absorb the sound much more. So, and finally looking at different enabling technology. One is McKeven muscles coupled with the EHT pump. So these are the fiber pump that can push the fluid and not a very rigid pump. Also different ways of printing different multi-materials. So one example I would like to share more detail is shape memory materials. So shape memory material, when heated, they just shrink. So that means you get 4 to 8% of actuation, but they are very compact, just like a wire. Just you heat it and you get lot of force. So very efficient. The challenge is once you heat them, it needs to cool for the next actuation, and that is the limitation we get with it. Some of the development we have done is a very compact actuator. It's just a two plastic pieces with the SMA in the middle. It can lift very high weight. And also some we have used the spring mechanisms, or some of the ideas you heard in the previous talk are similar ideas has been applied. And these are used for the seat. So we can have seat which can adjust the surface based on the occupant size or type of accelerations you are seeing. So it can improve the comfort. The other is to make a smart fabric. So when here is just an example of smart woven smart SMA. When it's heated, it will change shape. Depending on the weaving, you can get different shape. Or we can also use it with the fabric. So smart fabric, which can open pores when temperature is high or some other reason. So that's the kind of thought process. Now, other example was we have developed the fenders. So you have a wheel opening in the front wheel, and those are not very efficient because that can add a lot of drag. So the idea was, can we cover them? But then when you take a turn, then there is a problem. So we design a fender skirt using the SMA, and this fender skirt can open when it is actuated. So this is just the concept. So the idea is to use the SMA to create a very lightweight and compact hinges, and it can open, deform the fabric, and you can open them. Now another actuating material is a twisted coil polymer actuator, and you can just see here. So these are something similar to SMA, except that they are polymer, lightweight, and can be integrated with the fabric as well as polymer material. So they are very efficient. The negative is the forces it takes may not be as high. Now another example I'd like to share is using quasi-zero stiffness structure. Some of these we have seen in the past. And what it is a disc springs. These disc springs, when they have certain specific geometry, they will have a flat loading area. So you load it, they become flat, and then they start loading back again. So that's what these typical disc springs do. They are very low cost, very cheap material. And if you can stack them up, then you can create a nonlinear stiffness spring. So the non-linearity is pretty much like it loads, it becomes flat, and then it goes up. Now, when we use such non-linear spring, you can see it here. We have a vibration of the base, but the top is not vibrating. I think you saw similar example in the previous. And here is a transmission loss you can see. So there are many ways you can come up with QZS structure. We have been working with Ram and Suresh's group at ISE. They have been helping us, and there are many ideas has been investigated. Lattice structure, disc springs, or some simple combination of two springs with the bistable structure. So there are many ideas in being considered, and depending on the application, we can probably use those. So what we have now is we have one of the challenges that with this type of structure is the when when the mass changes, then we saw that about 5 to 10% it can handle it, but once the mass is higher, they are not as effective. So the idea was that can we adjust the stiffness, and this has been achieved by adding a stepper motor at the bottom. Stepper motor preloads the spring. As a result, many different non-linearity and with the QZS zone is possible. So this has been already demonstrated. The unit you can see is on the right side. It's a little bulky. And we also use such isolators for the headrest. And we found in the actual vehicle test as well as actual data that shows that there's a significant improvement, and people have on the sensor evaluation found it very helpful. And the next is we have one isolator, but what we are looking is we need to have if you use anything supported at four ends, we will probably have to make sure all the isolators work as a team. They connect with each other, and that's something we are looking for in the future. So the other example, jamming. We want to do jamming. Typically, jamming is done by using the rigid tiles, and they are inside the fabric package. And when the vacuum is applied, the tile, as you see here, they come and they kind of get jammed with each other. So something that is soft, it can become very rigid. Now here is an example. You can see this is when its vacuum is applied, this flat surface is becoming rigid, and the usage side, it can be used as a blanket that can be put it on a luggage, and then it becomes rigid, so that can be very, very stable. Or we are thinking it can be used to restrain people once they put it in, sit in the car, and we can have similar blanket which rigidizes when it's needed to protect the occupant. Okay, and then this is probably last example, the airbags. So airbags, when you have something hitting in the middle, they have one property, but if you hit it at the end, the properties are different. So the idea here is to use the tandem. So these tandems can restrain and change how the inflatable structures deform. And as a result, we can change its energy absorbing properties as well as control the stiffness. And here is just an example where we are hitting on the corner with and without the tandem structure, and that can show difference in how the energy absorption and forces are. And this is again concept development. The idea will be taken into airbags so they can perform better in all different conditions. So there are many examples. Time is limited, so I'm just going to not show all of them, but go to the key challenges. That these are our image. We would like to see some of these key challenges addressed. So one is we would like to see a 3D digital morphing surface, and the idea is something. Think of a plasma TV. Now, if you have a plasma TV, you have thousands of pixels, and each pixel you have different color and also brightness, and that is controlled by the voltage. So you give 300 volt voltage in each pixel. So electronic to do that is there. Of course, the current is very small in this case. Now, question is, can we come up with an EAP material and an array of EAP material, and each of these EAP material pixel is controlled by the voltage, can change the its shape, so it can become a little larger or smaller, and as a result, you can have a deformed surface. So that's one of the challenge we are looking for. And the other is we think there are very many possible applications for the pneumatics, and use the pumps and muscle like activity. So we would like to develop some kind of soft pump which doesn't have any hard parts and is very compact, something just inspiration from the heart. So we hope to see such technology in the future. And finally, the conclusion. Basically, we think the programmable material and physical systems are important in improving vehicle performance and safety. We can use it to personalize and also help robots, exoskeleton, etc. But to make these in the product or to use it, we need everything. We need actuator, sensor, flexible systems, etc. So everything needs to be worked together, and we are very open to new ideas. We are open to discussion. So do feel free to reach out to us. So that's the basic. That's the end of my presentation. And if you have any questions or any comments, feel free to make those. Thank you.
Thank you. Thank you, Dr. Gandhi, for the exciting presentation. We'll take one question in the interest of time. Anybody wants to ask a quick question?
Sure.
Yes. Thank you so much for your interesting talk. I have a question regarding the developing time. You talked about 20 years. Is it still like this? Because I was at the conference Doors and Closures, and it was a conference where mixed people, OEMs, and everybody was there regarding doors and closures. And it was amazing how fast China is developing. I think China cars are developed in 5 up to 10 years. Is this correct?
Okay. So let me explain to you. So car itself can be developed in 3 to 5 years. So once they say, okay, we want to make a next car, maybe next Camry, that is 3 to 5 years. But the technology development takes before. So what we are research. We take research, fundamental technology, and then say how can it be applied and that part. So we need to demonstrate, show the concept that it's feasible, it can be used. These are the limitations. Then next 3 to 5 years, it can be applied in the vehicle. So
Yes,
you're right.
yes, Germany also has some development regarding cars, probably.
Yeah.
But I talked with some engineers, and they
Mhm.
said the regulations are so strict, so regulated that it
Mhm.
takes so much time. But in China, it goes better. But maybe soon in India, there will be more fast.
Yeah, I agree. It's possible, but that's the basic idea. So let me show you. I have the chart here. Yeah. So basically,
Right. Thank you very much, Dr. Gandhi, for the presentation and Q&A. I would like to request Professor Sandeepan to present Dr. Gandhi with a token of appreciation from the organizing committee.
okay.
Thank you very much.
Thank you for the opportunity.
We'll now move on to the seminar halls 1 and 4 for the final technical sessions of the day. And at 6 o'clock, we will meet here again for the classical event, which is a Kuchipudi performance. We'll make a few announcements regarding tomorrow's proceedings in the seminar halls itself. Yeah, we can make a move to the seminar halls. Thank you very much.